Hello there, and welcome to Science for Sleep, where curiosity settles comfortably beside you, and the universe becomes something gentle enough to explore at the quietest moments of the night. As you get settled wherever you are, perhaps wrapped in a blanket or simply letting the day soften in your mind, tonight we're drifting into a story that stretches across unimaginable distances, yet arrives here with you in this very moment. It's a story that has been unfolding for billions of years, entirely indifferent to our clocks, calendars, or late-night yawns. And yet somehow there's something soothing about knowing that even galaxies move at their own unhurried pace. Because tonight, we're wandering into the future of our home, the Milky Way, and the path it's taking toward an enormous neighbour drifting ever closer, the Andromeda galaxy. They're not racing. They're not crashing in some explosive spectacle. They're simply approaching each other with a kind of cosmic patience, on a trajectory that has been quietly set long before humans ever looked up, to wonder why the stars seem so still. Before we begin to trace their motion through the vast dark, I'm curious where you're joining from tonight. What does the sky look like where you are, and what time is it in your corner of the world as you listen to this? Whether it's early morning, a late night, or something in between, I'm glad you're here. And if these slow explorations of the universe help you unwind, ease your thoughts, or drift towards sleep, I'd be grateful if you'd give the video a like or maybe subscribe. It helps this space stay calm and reach others who might be looking for a peaceful place to rest. So let's get comfortable and start at the beginning of this immense journey. Somewhere out there in the dark, far beyond anything the unaided eye can see clearly, two enormous structures of stars are drifting toward each other. Not with the violence you might imagine from the word collision, but with the steadiness of gravity acting over incredible distances. To picture their movement, it helps to remember just how much empty space there is between stars. Our solar system is a tiny island of light inside a galaxy that contains hundreds of billions of these islands. If you could shrink the sun down to the size of a marble, the nearest star would still be thousands of kilometers away. The Milky Way itself is a disk about 100,000 light-years across. That number often feels too big to hold in your mind because a single light-year is already unimaginably large. Yet even that giant disk is just one of trillions of galaxies in the universe, all drifting, swirling, merging and reshaping themselves over cosmic time. The Andromeda galaxy sits roughly 2.5 million light-years away from us. When you look at it through a telescope, you're seeing light that began its journey before the earliest humans walked the Earth. Andromeda is the only major galaxy besides our own that we can see with the naked eye from Earth, though it appears only as a faint smudge to most. That smudge represents a colossal city of stars larger than our own, moving toward us at about 110 kilometers per second. That sounds fast, and in everyday life it would be impossibly fast. But across the scale of galaxies, it's a leisurely drift. At that pace, the two galaxies won't meet for another 4 billion years or so. But even now, the future of that meeting is already written in their motion. They're bound by gravity, not in a sudden pull, but in a patient, steady approach, almost like two slow-moving islands of starlight gliding across a quiet ocean. When we imagine galaxies colliding, it's easy to picture something chaotic, full of crashing stars and explosions. But the truth is far more calm, which is why this story fits so comfortably into a sleepy exploration like this. Galaxies pass through each other with more grace than violence, because stars are spaced incredibly far apart. Even when the cores of the Milky Way and Andromeda eventually interact, most stars simply drift past each other. The main forces at work aren't direct impacts, but gravity stretching, pulling, and redistributing the paths of stars. Think of it less like two stones thrown together and more like two vast clouds slowly drifting into one another. Their shapes distort, their contents mix, new patterns form, and over time something new emerges. But before any of that takes place, before the first hints of distortion ripple through the Milky Way, there's the long quiet approach, the stage we're living in now. Everything in the universe that has mass creates gravity, and when things are separated by enormous distances, gravity becomes the slow curator of movement. The Milky Way and Andromeda sit in the same neighbourhood of space, part of a small cluster of galaxies adrift in the cosmic web. All of them are influencing each other ever so slightly, but the Milky Way and Andromeda are the pair locked in the strongest gravitational pull. Their motion is not aimless. Andromeda is heading toward us, and we toward it, drawn by a mutual attraction that has been unfolding since long before the Earth formed. Our solar system is positioned about halfway out from the centre of the Milky Way. That means as the galaxy moves, spirals, and eventually interacts with Andromeda, our Sun, and its planets come along for the ride. But none of this is something we need to worry about. Human civilizations rise and fall in the blink of a cosmic eye, and the changes that unfold in this story happen over spans so long that even entire species come and go before anything noticeable occurs. Still, there's something wonderfully humbling in knowing that our home galaxy is not a static object. It has a past full of mergers and collisions, and it has a future shaped by the next great encounter waiting billions of years ahead. As the galaxies draw nearer, there will come a time when the faint glow of Andromeda becomes more than a dim smear in the sky. Over millions of years it will grow brighter, more detailed and more impressive. If any distant descendants of humanity or whatever life exists then are still looking up at the night sky, they'll see a spectacle unfolding slowly across generations. Andromeda will stretch wider, revealing its spiral shape clearly, until one day it dominates the sky as a majestic arc of stars. The approach will paint the heavens with patterns no human alive today will ever see, and through all of it there will be no sudden shattering, no instant catastrophe, just the calm, steady pull of gravity rearranging the positions of stars and dust on scales too large for immediate drama. Even now, with telescopes and models and computer simulations, we can predict much of what will happen. Gravity is predictable at galactic scales. The motion of Andromeda can be measured with remarkable precision. By observing the subtle shift of light from its stars, astronomers know it is coming toward us and not merely moving sideways. This forward motion ensures that the galaxies will not merely pass by each other harmlessly. They are truly on a path to meet. But that meeting won't resemble the collisions we see in movies. Space is too empty, distance is too vast, and the force is too gentle on the scale of individual stars. The transformation will come from tides of gravity, pulling stars into new orbits, reshaping the disks, stretching long streams of stars outward, and eventually blending the two galaxies into one new structure. But before that blending happens, the story moves through several quiet phases. Long before the cores interact, the outer halos of dark matter, invisible but massive, will overlap. This soft boundary surrounding each galaxy plays a significant role in how they merge. Dark matter doesn't collide or clump like normal matter. It simply passes through itself, allowing the galaxies to begin overlapping without a physical impact. The stars, too, mostly pass through. Even the giant clouds of gas may flow around each other without dramatic collisions at first. The earliest changes will be subtle distortions, slight shifts in the shape of each disk, gentle arcs in the paths of stars at the edges. If there's something comforting about this immense process, it's how slow and steady it all is. There's no rush in the universe. Galaxies move at their own pace, and gravity works patiently. It's a reminder that even on the larger scales, the rhythm of change is gradual. Our everyday lives are filled with urgency, deadlines, alarms, and constant motion. But when you zoom out to the motion of galaxies, the entire tempo shifts. Everything stretches into calm, long arcs of time, billions of years between beginnings and endings, entire generations living within one tiny moment of a process that will continue long after we're gone. As the galaxies draw closer still, the pull between them strengthens. Over tens of millions of years, their shapes begin to warp. Spiral arms stretch, forming long tails of stars drawn out by gravitational tides. Stars that once orbited comfortably in neat paths find themselves tugged into new trajectories. Some are slung far from the merging pair, ejected into the darkness between galaxies. Others fall inward toward the growing centre of mass created as the galaxies interlock. If you were watching this unfold across deep time, it wouldn't resemble destruction. It would look more like two immense whirlpools slowly swirling together, their patterns twisting and folding into each other. And through it all, most stars remain intact, shining quietly as gravity guides them into their new place. All of this paints a picture not of chaos, but of transformation, a shift from one structure to another, a gradual reorganization guided by the simplest law of attraction, acting over extraordinary scales. It can feel strange to think about the future of the Milky Way in this way. Our home galaxy feels stable from our perspective. The stars we see seem fixed, but in reality everything is in motion. The Sun is orbiting the centre of the Milky Way at about 220 kilometers per second, taking more than 200 million years to complete a single orbit. The galaxy itself is drifting, rotating, influenced by the presence of dark matter and other galaxies nearby. Nothing is still, even if it feels that way when we look up into the night. The story of the Milky Way and Andromeda meeting is part of a much larger rhythm of cosmic evolution. Galaxies collide often throughout the universe. It's a normal part of their life cycle. Many galaxies we see today are already the product of past mergers, blended structures shaped by interactions long gone. The Milky Way itself has absorbed smaller galaxies over time, stretching out streams of stars that still linger like faint memories. Andromeda has done the same. Their upcoming meeting is not an anomaly. It's simply the next step in a process that has unfolded countless times across the cosmos. When you look up at the night sky, especially on a clear evening far from city lights, it can feel like the stars are close enough to count. They seem to sit side by side, sprinkled across the sky, like tiny lamps hung along some invisible ceiling. But the more you learn about what lies between them, the more you realise that distance in space is almost nothing like distance on Earth. The stretch between stars is not just empty. It's so empty that our everyday words for nothingness don't quite capture it. An understanding that quiet openness is one of the keys to understanding why a collision between the Milky Way and Andromeda will be so calm, so strangely gentle, and so different from anything the imagination tends to invent when it hears the word collision. It helps to start small, at the scale of our own solar system. You might picture the planets orbiting the Sun like a tight family of worlds clustered together, but the truth is much more spacious. If the Sun were shrunk to the size of an ordinary door, Earth would be a grain of sand floating a few meters away. Jupiter would be another pebble even farther out, and beyond that, the space separating each planet stretches wider and wider until the entire system begins to feel like a scattering of islands in a vast, calm sea. Even the Sun's closest neighbour, Proxima Centauri, is more than 4 light-years away. That distance is so large that if the Sun were a marble, Proxima Centauri would be another marble sitting roughly 100 kilometres away. Between them lies nothing solid, nothing visible, nothing to bump into, just an expanse so empty it becomes difficult to hold in the mind for long. Now take that emptiness and scale it up to the size of a galaxy. A galaxy like the Milky Way contains hundreds of billions of stars, each surrounded by its own bubble of space, each drifting in orbits that take millions of years to complete, each maintaining enormous distances from its neighbours. If you stood in the centre of an imaginary version of the Milky Way where stars were shrunk to the size of ping-pong balls, you would still have to walk kilometres between them. And that's not because the galaxy lacks material. It's full of gas, dust, dark matter and stars. But the scale is so large that all of that matter becomes thinly spread across an enormous volume. Most of a galaxy is transparent because it's mostly space, not stars. Even the bright, dense-looking bands of the Milky Way that appear in the night sky are still composed of stars sitting incredibly far apart. This quiet openness is the reason galaxies can pass through each other, without stars smashing together like billiard balls. When galaxies meet, the chance of two stars making direct contact is incredibly small. For all their beauty and brightness, stars are tiny compared to the distances separating them. The main forces at work during a galactic encounter are not collisions of objects but interactions of gravitational fields. Stars influence each other from afar, tugging gently or pulling dramatically depending on their positions, but they almost never touch. This is why, when you imagine the Milky Way approaching Andromeda, the drama plays out not in bursts of impact, but in long, slow waves of motion. Even giant clouds of gas inside galaxies, which are far more spread out and diffuse than they look in pictures, rarely collide head-on. They may pass through each other, triggering bursts of star formation or changing shape. But even then, the process is governed more by gravity and gentle pressure than by catastrophic impacts. The space between particles inside those clouds is huge. A cloud that looks dense when photographed in visible or infrared light is actually so thin that if you took a volume of that cloud, the size of a room, it might contain only a few molecules. Dense by cosmic standards, yes. Dense by human standards, not even close. The emptiness between stars is one of those truths about the universe that feels almost philosophical once you sit with it long enough. For all the light we see, the universe is overwhelmingly made of space, not of things. And the things that do exist inside that space are separated by distances so wide that entire solar systems could drift for billions of years without coming close to a neighbouring star. This is why the Milky Way and Andromeda, each containing hundreds of billions of stars, can begin gliding into each other with so little physical disruption. Their stars travel freely through the surrounding emptiness, guided only by gravity. To picture this emptiness in a way that isn't just numbers, imagine a single star like the Sun floating in space. Now imagine drawing a sphere around it with a radius of 1 light year. That sphere would be unimaginably large, something like 10 trillion kilometers from edge to edge. Now remove the Sun from the picture and place a single grain of salt at the center. That grain of salt represents the Sun, and now add one more grain somewhere on the surface of the sphere to represent the nearest star. Everything in between is empty. That's the level of spacing we're dealing with inside galaxies. But emptiness doesn't mean nothing happens there. Space is full of invisible influences. Gravity operates across even the widest gaps. Light travels freely through most of the distances. Electromagnetic fields from stars stretch outward into the void. And the motion of galaxies themselves is guided by enormous halos of dark matter that are not empty at all, even if they're invisible. Dark matter halos are vast spherical regions surrounding galaxies, containing far more mass than the stars and gas we can see. These halos influence the motion of stars, shape the structure of galaxies, and play a major role in how galaxies interact during mergers. The quietness of space is what allows galaxies to move smoothly through each other without breaking apart violently. But that same quietness hides the enormous influence of gravity. Gravity is subtle, but its reach is infinite. A star doesn't need to be close to another star to feel its pull. It just needs to exist. And when billions of stars move in the same general direction, their combined gravity becomes a force powerful enough to reshape entire galaxies. When we say the Milky Way and Andromeda will collide, that collision is really a gravitational event. The empty space between their stars doesn't prevent the merger, it simply determines its nature. Inside the Milky Way, the emptiness between stars makes our galaxy a surprisingly peaceful place on the scale of stellar lifetimes. Stars rarely threaten each other. Planetary systems remain stable for billions of years. Solar systems can orbit the galactic center many times without encountering a rogue star. But during a galactic merger, that long-distance calmness starts to shift. Stars don't hit each other directly, but their orbits can change dramatically. A star that once orbited steadily in the Milky Way's spiral arm might be pulled into a new path by Andromeda's gravity, or it might be flung out into intergalactic space, becoming a lonely traveller drifting through the void. These changes happen without collisions, They happen because the gravitational landscape changes. If you were to place yourself somewhere inside the Milky Way during its approach toward Andromeda, you wouldn't feel the emptiness between stars. Everything around you would look the same as it always has. The sun would rise and set on Earth. Stars would drift across the night sky. Nothing would suggest that entire galaxies were moving toward each other, and that's because the distances are so large and the motion so slow that even across millions of years, any visible change happens almost imperceptibly. The merging of galaxies is a drama played out on a timescale our minds are not built to track. The events unfold not over months or years, but over spans so long that even mountains rise and erode multiple times before the galaxies begin to truly overlap. This quiet vastness is the stage on which the entire story of the Milky Way and Andromeda's meeting unfolds. It's what allows the merger to be both enormous and gentle at the same time. The galaxies will pass into each other almost like ghosts, their stars flowing through the surrounding emptiness, influenced not by impact but by gravity. That's why astronomers can simulate their merger so effectively. The physics are predictable. There are almost no messy collisions to account for. Instead, the stars behave like particles drifting in a slow, complex dance, guided by the changing shape of the gravitational field. Understanding this emptiness changes how you imagine the future of our galaxy. It shifts the picture away from dramatic destruction and towards something more like a long reorganization. Stars will migrate. Orbits will twist. The shape of the galaxy will stretch, but almost none of the stars themselves will be harmed. This is why the Sun, even though it may be pulled into a new position, will almost certainly survive the process. The Earth, if it still exists, will orbit the Sun just as it always has, unaffected by direct collisions but influenced by the changing gravitational environment. The emptiness between stars is also why space travel remains such a challenge. Even though stars seem close when viewed from Earth, they are separated by distances so vast that even the fastest spacecraft would take tens of thousands of years to reach the nearest one. This emptiness doesn't just define galactic mergers, it defines our reality as inhabitants of a single star system. It shapes our sense of isolation and our sense of wonder, because every point of light in the sky is both astonishingly distant and part of a larger structure held together by the most subtle of forces. When you look at two galaxies drifting toward each other across the dark, it can feel natural to assume they made a decision somewhere along the way, as if one turned its spiral arm slightly to the left, the other adjusted a little to the right, and now they're slowly aiming themselves at one another like ships approaching in the night. But galaxies don't operate with intention or plans. Their paths are the result of motion set in place long before the Earth, the Sun, or anything familiar to us existed. The Milky Way and Andromeda have been travelling through space for billions of years, and the story of how they ended up on a collision course is something that began not with the galaxies themselves, but with the earliest distribution of matter after the Big Bang. It's a story that stretches back to the birth of structure in the universe, when everything was still settling into the shapes that would later become galaxies. After the universe expanded from its earliest hot, dense state, matter wasn't spread perfectly evenly. Some areas contained slightly more mass than others, tiny differences too small to notice if you looked at the early universe the way you might look at a map. But gravity notices even the faintest imbalance. Wherever matter gathered just a little more densely, gravity pulled more matter in, and over hundreds of millions of years those small fluctuations grew into clumps. Those clumps became the first galaxies, formed as swirling halos of dark matter attracted gas, dust, and eventually the first stars. The Milky Way and Andromeda were born from two such clumps, seeded by these early variations in density, each settling into its own region of space as the universe expanded. Even in these early days, the galaxies weren't isolated. Everything in the universe pulls on everything else, though the strength of the pull depends on distance. The Milky Way and Andromeda formed in the same region of the cosmic web, the vast network of filaments and clusters that defines the large-scale structure of the universe. In this network, galaxies are not scattered randomly. They tend to group together in clusters and small collections. Our own part of the universe contains a modest group of galaxies called the local group. It's not large by cosmic standards, just a neighbourhood of a few dozen galaxies bound together by gravity. And at the centre of this neighbourhood sit the two largest members, the Milky Way and Andromeda. The motion that eventually set them toward each other began billions of years ago, when both galaxies were still forming. They were never truly stationary. As they grew, their surrounding dark matter halos expanded. Dark matter is the invisible scaffolding that gives galaxies their structure. It doesn't shine or reflect light, but it provides most of the mass that shapes how galaxies move. As these halos formed, they exerted gravitational influence on one another. Even when the visible parts of the Milky Way and Andromeda were still small and faint, their halos were already pulling on each other across the expanding universe. This gravitational influence didn't overpower the expansion of the universe itself. Space was stretching, galaxies were receding from each other, and everything was moving outward from the Big Bang. But on smaller scales, like inside the local group, gravity could overcome that expansion. The Milky Way, Andromeda, and the other nearby galaxies were close enough that their mutual gravity slowed the expansion between them, until eventually they began drifting closer overall. Not fast, not dramatically, and not in a straight line. Their paths curved gently, shaped by the pull of many objects, the dark matter halos, the smaller galaxies orbiting around them, and even the motion of the universe expanding around them. If you could rewind the motion of the local group like a film and watch it run backward, you would see the Milky Way and Andromeda moving in complex arcs. They wouldn't look like two objects directly aimed at each other. Instead, they would trace winding paths through space, gradually circling and approaching, influenced by countless little gravitational nudges. Over time, these nudges added up. The expansion of space between them slowed, then stalled, and eventually reversed. At some point billions of years ago, their separation reached a tipping point. Gravity became the dominant force between them. From then on, the long, slow approach was set. It's important to understand that galaxies don't move like ships gliding across still water. They move through a medium shaped by the gravitational field of everything around them, including dark matter we cannot see directly. The local group is filled with smaller galaxies, remnants of older mergers, streams of gas and stars that have been torn apart over time, and vast halos overlapping and interacting. These structures shape the motion of the Milky Way and Andromeda. Their paths were not carved with precision, but with the complexity of billions of years of gravitational influence. At the scale of the local group, space behaves a bit like a landscape with hills and valleys made of gravity. The galaxies roll through this landscape, guided by the contours carved by mass. The Milky Way and Andromeda sit in a kind of valley together, created by their combined gravity and the dark matter halos surrounding them. They were never destined to drift apart indefinitely. They were always part of the same gravitational basin, pulled gently toward one another. Once both had grown large enough and slowed relative to each other enough, the direction of their overall motion became clear. They were on intersecting paths. Astronomers know this not from watching them move over the short period of human observation, but from measuring the light they emit. Light from distant objects shifts depending on whether the object is moving toward us or away from us. This effect is called the Doppler shift. When Andromeda's light is analysed, its wavelengths are slightly compressed, meaning it is approaching the Milky Way. That tells us about its motion along our line of sight. For many decades, that was all we had. Andromeda was moving toward us directly, but we didn't know whether it also had sideways motion that might cause it to miss us entirely. More recent observations solved this. By tracking the positions of stars in Andromeda with extreme precision using multiple telescopes, astronomers were able to measure tiny sideways movements across the sky. It turns out Andromeda isn't just moving toward the Milky Way. It is moving toward nearly the exact region of space where the Milky Way is also headed. The sideways component is small, not enough to cause a harmless pass. The two galaxies are on a direct, inevitable path toward each other. Not because they steered themselves that way, but because gravity gradually drew their motions together. But the deeper cause stretches even farther back. The motion of galaxies today is the result of the early distribution of matter in the universe. The Milky Way and Andromeda, forming in close proximity inside a shared gravitational space, were always going to interact eventually. That interaction may have happened sooner or later depending on countless small influences, but the overall direction of their paths was set by where they formed and how gravity shaped their region of space. Their motion wasn't something that changed suddenly. It was the result of billions of tiny adjustments, each guided by gravity acting over enormous distances. Another factor in their meeting comes from the motion of the universe itself. While the universe overall has been expanding since its beginning, that expansion does not pull galaxies within gravitationally bound groups apart. Inside the local group, gravity is strong enough to counteract expansion completely. The Milky Way and Andromeda aren't being pushed away from each other by expanding space. They're held together. If gravity weren't present, if the galaxies were not bound inside this group, they would drift apart just like most galaxies in the universe. But bound structures act differently. Inside these regions, gravity has the final say. When the Milky Way formed, it already had smaller galaxies orbiting it, some of which were pulled in and merged over billions of years. The same is true for Andromeda. Over time, both galaxies grew larger and more massive, strengthening the gravitational attraction between them. The more massive objects become, the stronger the pull between them. Their halos expanded, their influence on each other deepened. The dark matter that surrounds both galaxies created a gravitational envelope that gradually tightened the space between them. When we observe their positions today, we see two galaxies separated by about 2.5 million light-years. But that number only describes the present moment. In the past, the distance was larger. Billions of years ago, they were farther apart, moving in more complex paths. But as the universe aged, the gravitational pull between them accumulated. Like two heavy objects placed on a slightly sloping surface, they began to slide toward the center of the gravitational valley they share. The slope is gentle, the motion slow, but over billions of years it's enough to bring them toward each other. There's a certain calmness in imagining this motion. Nothing dramatic ever happened to set their path. No sudden push, no singular event. Just gravity, working quietly across the history of the universe, drawing two galaxies closer one tiny step at a time. The path was not a straight line. It was a long, meandering drift, shaped by growth, mergers, dark matter, and the underlying geometry of their shared place in the cosmic web. Even now, the motion continues. Andromeda is approaching at about 110 kilometers per second. That sounds incredibly fast, but compared to the size of galaxies, it's almost leisurely. If you could watch the two galaxies move toward each other in real time, the motion would be invisible to the eye. Only the measurements made over decades reveal the subtle change. This speaks to the scale of the story. Entire human histories unfold while galaxies move the tiniest fraction of the distance that separates them. Yet the motion never stops. It's always happening, always changing, always pulling them closer. Understanding how the Milky Way and Andromeda set their course also helps explain why galactic collisions are common. The universe is full of small groups like ours. Galaxies form in clusters, interact, merge, and reshape each other. The Milky Way itself contains leftover traces of past collisions in the form of star streams and disrupted dwarf galaxies. Andromeda has similar evidence. These events are part of the life cycle of galaxies, driven by the same forces that will eventually bring the Milky Way and Andromeda together. When people imagine two enormous objects on a collision course, the mind tends to fill in the blanks with images of sudden impact, noise, force, and destruction. It's natural. On Earth, When two things crash into each other, the consequences are immediate and unmistakable. A glass hits the floor and shatters instantly. Two cars collide and deform in a fraction of a second. Even something as simple as a dropped book makes an unmistakable sound the moment it touches the ground. We're used to events that happen quickly, because our daily experience is filled with sudden changes. But the universe operates on a completely different scale, and the way galaxies meet each other is almost the opposite of anything we witness here. When the Milky Way and Andromeda eventually come together, it will not resemble an impact at all. It will unfold so slowly and over such an immense period of time that calling it a collision almost feels misleading. It's more like a long, patient rearrangement than anything resembling a crash. To understand how slow this process truly is, it helps to begin by thinking about the sheer distance separating the two galaxies. Right now, Andromeda is about 2.5 million light-years away from us. That distance is so enormous that light, which moves faster than anything else in the universe, still takes millions of years to cross the gap. If a beam of light left Andromeda at the moment you were born, it would still be nowhere near arriving by the time you reach middle age. Andromeda's current speed toward us is about 110 kilometers per second, which sounds fast in ordinary terms, but compared to the scale of the distance between galaxies, it's leisurely. If you were to shrink the distance between the Milky Way and Andromeda down to the size of a football field, Andromeda would be drifting toward the Milky Way by less than the width of a grain of sand each second. It's steady, measurable and undeniable, but it's not fast. This overwhelming slowness is what defines the entire encounter. Every stage of the meeting, from the first subtle distortions of the galaxy's shapes to the final settling of their merged form, spans periods of time that are impossible to relate to anything in a human lifetime. The galaxies will spend hundreds of millions of years drawing nearer. Then they'll begin to overlap. Then they'll separate again slightly. Then they'll fall together once more. The entire process, from the moment they begin to influence each other visibly to the moment the new galaxy reaches its final shape, will take several billion years, not thousands, not millions, billions. That's longer than the Earth has had complex life, longer than mammals have existed, longer than it took for the sun to form from clouds of gas and dust. When we say this is the slowest collision in the universe, it's because any reasonable definition of a collision barely applies. If you could somehow observe the meeting of the galaxies in real time, it would look static. Nothing would move. The stars would continue shining in their familiar positions. The Milky Way's spiral arms would hold their shape. Andromeda would remain a faint blotch in the sky. Even if you spent your entire life watching, you wouldn't notice a single thing change by eye. The collision is so slow that the entire timeline of humanity fits into a tiny slice of it. Civilizations rise and fall, languages evolve, species appear and vanish, and through all of it, the galaxies continue their approach, but at a rate so small that a human lifetime doesn't register the tiniest fraction of it. This extraordinary slowness is partly a result of the enormous scale of space, and partly a result of the nature of gravity. Gravity is powerful, but it works patiently. The force between the Milky Way and Andromeda is strong enough to draw them together, but they are so large and so distant that the process cannot unfold quickly. Each galaxy contains hundreds of billions of stars held together by a delicate balance of motion and gravity. If everything were pulled too quickly, the galaxies would tear themselves apart. Instead, the universe follows a rhythm that preserves structure while still guiding everything toward the final outcome. Gravity applies constant pressure, but not in a way that produces sudden rearrangements. It gently nudges, adjusts, and tugs. Over billions of years, these small influences accumulate, shaping the path of the galaxies like a slow tide shaping the coastline. When the galaxies finally become close enough to interact, the slowness continues. The first signs of the encounter won't be collisions but distortions. The outer regions of the galaxies will stretch. Their shapes will begin to warp gradually. Stars in the outskirts will feel the combined pull of two enormous gravitational sources instead of just one. This won't happen quickly. It will begin with faint adjustments, barely perceptible compared to the overall structure. Spiral arms may tilt slightly, the edges may ripple. Over millions of years, the distortions will grow more noticeable, but they still won't resemble anything sudden. These early changes are so drawn out that if you place snapshots of the galaxy millions of years apart, you could begin to notice the difference. But in real time, nothing would appear to move. Eventually, the galaxies will draw close enough that their visible parts begin to overlap. But even this stage won't feel like a collision. When galaxies overlap, the stars simply pass through each other because the space between them is vast. The galaxies from far away give the impression of being dense because they contain so many stars. But the distances between those stars are enormous. They're like specks of dust drifting in a volume the size of a planet. If the Milky Way and Andromeda were oceans, each star would be a single drop of water separated by the entire ocean itself. With spacing like that, the stars travel through the combined structure without touching. The galaxies pass into each other like two drifting clouds. The first pass-through is surprisingly uneventful in terms of direct contact, but gravity is busy during this stage. It's not the stars bumping into each other that matters, but the way the overall gravitational landscape changes when two massive systems overlap. Stars that once followed stable orbits around the centre of the Milky Way will find themselves pulled by Andromeda's mass. Stars in Andromeda will feel the same pull from the Milky Way. Their paths will begin to change slowly. Some stars will be flung outward into long streams that stretch into space. Others will be pulled inward, deepening the gravitational well at the centre of the merging structure. These changes create the chaotic appearance seen in images of galaxy interactions, but even this chaos unfolds gradually. Individual stars don't suddenly change direction. Their paths bend slowly over millions of years. As the galaxies pull through one another, they won't merge immediately. The momentum of each galaxy carries it forward, so they will drift apart again after the first passage. Imagine two large groups of people walking through each other slowly in a wide field. They pass through, continue walking, and eventually begin turning back toward each other because they're tied together by ropes. The galaxies have no rope, of course, but gravity plays the same role. After the first passage, they'll begin to slow again, then drift back toward each other. This back and forth motion could continue several times, depending on the exact paths and masses involved. Each pass-through distorts them further, stripping material, twisting shapes, and mixing their stars. But no pass-through is fast. Every part of the process takes millions of years. This slow dance is far more common in the universe than one might expect. When astronomers observe the sky, they see many galaxies caught in this process. Some are in the early stages, their shapes beginning to warp. Others are fully overlapping, with long streams of stars flowing outward. Some are deep in the final phase, forming large elliptical galaxies that are the result of earlier mergers. The Milky Way and Andromeda are simply the next pair in this long sequence of cosmic events. They're not unusual. They're not even rare. Galaxies merge because that's what happens to galaxies over time. They grow, collide, combine, and reshape themselves. One of the most interesting parts of this process is how star formation changes during a galaxy encounter. When galaxies pass through each other, the gas inside them can be compressed, triggering the formation of new stars. This doesn't happen suddenly. It happens slowly as clouds of gas press against each other or are nudged by gravitational tides. Over millions of years, these conditions create bursts of star formation. Entire new generations of stars may be born during the merger, adding fresh light to the combined system. This increase in star formation is one of the few ways the collision will have a dramatic visual impact, though even this unfolds gradually. There won't be a sudden brightening of the sky, but a slow increase in regions where stars are forming. These bright regions may form arcs or clouds of light visible across the merging galaxies. The slowness of the collision is also what allows planets, solar systems, and even life to remain unaffected by direct impacts. The Sun, for example, is expected to survive the merger without colliding with any other star. The chance of such a collision is extremely small because of the enormous distances between stars. The Earth, if it exists during the merger, will likely remain in orbit around the Sun. The gravitational environment around the solar system may change gradually, but nothing sudden will happen to disrupt the orbit. From the perspective of an observer living on a planet, the sky would change slowly over millions of years. Patterns of stars would shift, distant galaxies would appear closer, and eventually the shape of the Milky Way would alter. But no catastrophic events would occur just because the galaxies are merging. The slowness of the process protects everything on smaller scales from sudden upheaval. This enormous timescale also reveals something about the nature of the universe. Big events don't always happen quickly. The universe isn't filled with sudden explosions or immediate consequences. Most changes unfold over spans of time that make every human era look brief. Even the dramatic events we see in space, supernovae, collapsing stars, collisions of neutron stars, happen against a backdrop of much slower motion. The universe is quiet, patient, and methodical. It doesn't rush. It doesn't leap. It simply moves forward at its own pace. As the collision continues over billions of years, the shapes of the galaxies will shift from well-defined spirals into more irregular forms. Spiral arms will stretch and distort. The outlines of the galaxies will blur. Over time, the galaxies will lose their identity as separate systems. They will merge into a single, larger structure. But even this final stage won't come as a sudden transformation. The new galaxy will take time to settle into its final shape. It will grow rounder, less structured, and eventually resemble a large elliptical galaxy. The process of settling could take another billion years or more. Every stage of this event is measured in spans that stretch far beyond anything familiar on Earth. When two galaxies finally begin to meet, the word collide suggests something far more violent than what truly occurs. It brings to mind objects crashing together, explosions erupting, debris flying outward in every direction. But galaxies are not solid bodies. They're not like stones that break or metal that bends. They're immense swarms of stars, dust, gas, and dark matter, drifting through a space so open that even their most crowded regions are mostly empty. So when galaxies collide, the events that unfold are guided by gravity rather than impact, and the changes that happen, though dramatic when viewed across millions of years, are gentle in the moment. Understanding this difference makes the entire encounter easier to imagine, not as an abrupt disaster, but as a slow transformation. When the Milky Way and Andromeda begin to overlap, the first thing that happens is not a burst of destruction. Instead, their shapes change. Spiral galaxies like ours are organised systems with arms, bars, rotating disks, and central bulges. These structures exist because each star follows a path determined by the galaxy's gravitational balance. As soon as the galaxies start affecting each other, this balance shifts. Stars that once orbited in stable patterns begin drifting into new paths. The outermost regions feel the first pull, stretching outward into long arcs that can span hundreds of thousands of light years. These arcs, known as tidal tails, are one of the most visible signs that galaxies are interacting. They form because different parts of each galaxy experience different gravitational forces. The stars on the edges are pulled in directions slightly different from those closer to the centre, and over millions of years this creates streams of material stretching far into space. These tidal tails don't appear suddenly. They begin as subtle distortions and grow gradually. They're not solid structures. They're collections of stars and gas pulled into elongated shapes. In images of interacting galaxies elsewhere in the universe, these tails often look like delicate threads or smooth bridges between the merging systems. Some may curve gracefully outward. Others might loop around, forming faint rings or extended wisps. They tell the story of the galaxy's paths. each tail reflecting the motion of countless stars responding to the evolving gravitational landscape. If you could pause the universe at one moment during the merger and look at the two galaxies, you'd see these tails slowly stretching, expanding and curling in different directions. They're evidence of the quiet tug of gravity working across enormous distances. Inside the galaxies, another change begins. The gas within each galaxy is not arranged perfectly. It collects in clouds, some small, some large enough to form thousands of stars. When galaxies interact, these clouds pass through new gravitational environments. Some may become compressed as one galaxy's gravity pushes them against the gas of the other. Others may shift into regions where they feel stronger pressure. Gas is far more reactive than stars because it can collide with other gas, change temperature, and clump together. When these clouds are compressed, they can begin collapsing under their own gravity, triggering waves of star formation. This is one of the most important consequences of galactic collisions. Entire new generations of stars are born. These bursts of star formation don't light up the galaxies all at once. They emerge gradually in different regions. Some areas might become bright with clusters of hot young stars illuminating the surrounding gas. Other regions might remain quiet. Over millions of years, pockets of intense activity appear throughout the merging system. These bursts can last for long periods, though individual stars form quickly in cosmic terms. Some of the brightest regions may form thousands of stars in short intervals before fading as the gas is used up. The result is a complex pattern of activity that makes the merging galaxies appear more vibrant and lively. As the star formation increases, the shapes of the galaxies continue to warp. The gravitational centers of both systems shift as mass redistributes. Dark matter halos overlap, altering how stars move. The central regions of the galaxies, where stars are most densely packed, begin interacting more strongly. This doesn't cause collisions between stars. Even in the central bulges, the distances between stars are still vast. But the gravitational influence becomes more intense. Stars can be pulled closer to the merging core. Some may be flung outward if they pass through regions where multiple gravitational forces intersect. Others may fall toward the growing center, increasing its density. At this stage, the galaxies may begin to lose their familiar spiral shapes. Their arms become twisted. Their disks tilt or warp. The outlines become irregular and uneven. The galaxies no longer look like neat rotating systems. They look more like sprawling clouds stretched in different directions. This kind of distortion is common in interacting galaxies, and astronomers see it often in other systems at various stages of merging. The Milky Way and Andromeda will undergo something similar. Their once separate structures will blend together into a larger, more complex formation. Throughout this process, the Sun and its planets would continue orbiting calmly. The solar system might feel changes only in the form of subtle shifts in its path relative to the center of the combined gravitational system. Because stars rarely collide directly, the solar system will almost certainly avoid a disruptive encounter. It could be pulled into a new orbit around the merging galaxy's center. It might swing outward or inward depending on the mass distribution, but nothing sudden would happen. The planets would continue orbiting the Sun, and the sky would gradually change as the shape of the galaxy evolved. The night sky could brighten in some regions as new star clusters form, or become more crowded with streams of stars twisting across space. These changes would be slow and continuous. As the galaxies move deeper into each other, gravity becomes the dominant architect. The motion of stars grows more chaotic in certain regions. Some stars are ejected entirely, sent drifting into intergalactic space. These stars become part of a population of lone wanderers that float between galaxies indefinitely. Others are drawn inward, where the merging gravitational centers begin forming a more massive core. This core is not a single object at first. It's a region where stars orbit in dense, complex patterns influenced by two supermassive black holes, one at the center of the Milky Way and one at the center of Andromeda. These black holes won't immediately merge. They'll orbit one another at first, spiraling closer over millions of years. Their combined influence will deepen the gravitational well at the heart of the merging galaxies, drawing stars inward and shaping the motions of everything around them. Eventually, the black holes will get close enough that gravitational radiation becomes significant, causing them to lose energy and drift closer until they finally merge. That final merger is one of the few moments in this entire event that would release a burst of energy detectable far across the universe. But even that process is not something that disrupts stars directly. It unfolds quietly from the perspective of everything else. While all this is happening in the core, the outer regions continue to respond to the evolving gravitational field. Stars that were once part of the neat spiral arms of the Milky Way may be pulled into long looping orbits that carry them far from their original locations. Some may oscillate up and down through the combined disk. Others may find themselves in positions where they feel the gravitational pull of the merging system unevenly, causing their paths to bend or twist. As millions of years pass, the merged system begins to settle. The chaotic orbits smooth out. The tidal tails stretch into long, thin streams that slowly disperse. Gas clouds collapse or drift apart. The new stars that form during the interaction settle into clusters or drift away depending on their initial conditions. The shape of the resulting galaxy will be noticeably different from the two spirals that created it. Spiral galaxies tend to transform into more rounded shapes when they merge. The orderly rotation that defines a spiral becomes disordered by the blending of two separate systems. Over time, the composite galaxy becomes smoother, rounder, and more elliptical. The orbits of stars go from being neatly aligned in a spinning disk to being spread out in various directions. The central core becomes more massive. The outer regions become more diffuse. The overall structure resembles the large elliptical galaxies seen in many clusters throughout the universe. This entire transformation is what actually happens when galaxies collide. They don't smash together in a sudden burst. They interact gravitationally. They distort each other. They trigger waves of star formation. They exchange material. They blend their structures. They reshape the paths of their stars. And after a long sequence of these interactions, they settle into a new form. Not instantly, not dramatically, but inevitably, with every motion guided by gravity. Throughout all of this, the universe remains calm. There's no sound in space to mark the event. There's no shockwave spreading outward. There's no boundary where one galaxy crashes into the other. The collision is a gravitational ballet, played out on timescales so enormous that even entire species could rise and fall without seeing a single moment of rapid change. It's both serene and complex, a reminder that the universe evolves through quiet processes that unfold so slowly that they're invisible on the scale of human life. When you think about two galaxies moving toward each other, each carrying hundreds of billions of stars, it can feel almost impossible to imagine how they avoid smashing together in enormous bursts of energy. The mind naturally fills in the gaps with images of countless stars colliding like marbles pouring out of two jars shaken together. But the reality is so different from that picture that it almost feels like a trick of nature. Even when two galaxies pass directly through each other, the stars inside them almost never touch. Not because stars are fragile or because galaxies somehow dodge one another, but because space is constructed in a way that makes these collisions extraordinarily unlikely. When we explore why stars rarely crash into each other, we begin to understand not just the serenity of galactic mergers, but the true scale of the universe. To picture this properly, it helps to start by imagining the Sun as a single glowing sphere drifting in the dark. The Sun is enormous by everyday standards, with a diameter of about 1.4 million kilometers. But compared to the distances between stars, the Sun is small. The nearest star to us, Proxima Centauri, is more than 4 light-years away. A light-year is about 10 trillion kilometers. That's such a large distance that even the fastest spacecraft built by humans would take tens of thousands of years to travel it, So the distance between the Sun and its nearest neighbour is not just a little bigger than the Sun itself, it's millions of times bigger. If the Sun were the size of a marble, Proxima Centauri would be another marble placed more than 100 kilometres away. Everything in between those two marbles would be empty space. When you scale this up to the size of the Milky Way, the emptiness becomes even more remarkable. The Milky Way contains somewhere between 100 billion and 400 billion stars. That sounds crowded, but the galaxy is so large that the stars are extremely far apart. Even in regions where star density is higher, near the centre or inside dense clusters, the distances between stars remain enormous. If you could shrink the entire Milky Way down to the size of a country, the stars would still be separated by kilometres. It's a galaxy made not of tightly packed material, but of isolated islands floating far from each other. This vast separation is the fundamental reason stars rarely collide. To have a collision, two stars would need to pass so close that their surfaces touch. But because the distances between them are so huge compared to their physical sizes, the chance of such an encounter is vanishingly small. To get a sense of the odds, imagine filling a stadium with grains of sand placed meters apart from each other. Now imagine two such stadiums drifting through each other. The sand grains won't hit each other because they're simply too spread out. Galaxies behave in a similar way. They look solid in photographs because the stars are so bright and the images are taken with long exposures. But the brightness hides the emptiness. The stars inside galaxies act more like drifting particles in a vast void, barely interacting physically even when the galaxies themselves overlap. Another way to understand this is to consider how much empty space surrounds a typical star. The solar system alone contains enormous stretches of space with nothing in them. Most of the volume of the solar system is empty. Even the region where planets orbit is mostly void. The planets themselves are tiny compared to the space between them. When you think about the overall structure, the entire arrangement seems almost delicate, as if everything exists with plenty of room to move. When two galaxies pass through each other, the vast majority of their stars simply keep following their paths, influenced only by gravity. It's gravity that guides the interaction, not physical collisions. Gravity plays a key role in explaining why stars rarely hit each other. When two galaxies meet, their gravitational fields blend. Stars feel this blended field and change their orbits accordingly. But stars are small enough and far enough apart that their gravitational influence on one another is weak unless they get extremely close. The galaxy as a whole shapes how stars move, not the stars individually. That means during a collision, the orbits of stars shift on large scales, but only because the shape of the galaxy's gravitational field changes. Stars do not move toward each other for physical contact. They move according to the smooth curves of gravity that now include two galaxies instead of one. In some regions of the galaxy, stars are more tightly packed than others. Near the centre of the Milky Way, the density is higher. In globular clusters, it is higher still. These clusters are spherical collections of stars that orbit the galaxy in its halo. They contain hundreds of thousands of stars packed into a relatively small volume. Even in these dense environments, collisions between stars remain rare. The distances between stars and globular clusters are much smaller than in the galactic disk, but still vast enough that direct collisions don't happen often. A cluster might go billions of years without a single collision. Sometimes stars do pass close enough to influence one another's orbits, and occasionally they exchange momentum or shift paths. Sometimes they even form binary systems where two stars orbit each other, because their encounter was slow and gentle enough. But actual crashes, where stars merge violently, are extremely uncommon. When stars do happen to collide, the events are spectacular but rare. Collisions can create larger stars, cause bursts of energy, or in extreme cases produce explosions. These events are so infrequent that when astronomers observe a star that appears to have unusual properties, such as being unusually massive or having strange chemical signatures, one possible explanation is that it might be the product of a past merger. But these cases are exceptions, not the rule. They are fascinating because they are rare. They tell us that collisions are possible, but they also remind us how unlikely they are within the vastness of a galaxy. The emptiness between stars is not just a quirk of our galaxy, it is a fundamental property of the universe. Stars form inside clouds of gas that begin dense but expand outward. Gravity shapes these clouds, causing them to collapse and form star clusters. Over time, these clusters disperse. Stars drift apart. The majority of stars that form together eventually end up spread across large regions. Because the universe is expanding and galaxies themselves move within the cosmic web, the distances between stars generally increase as cosmic time goes on. So the overall pattern is one of increasing separation, not increasing density. This reinforces the idea that collisions will remain rare even during galactic mergers. When the Milky Way and Andromeda begin to overlap, the stars inside each galaxy will not rush toward impact. Instead, their motion will be shaped by the gravitational influence of the merging mass. Stars from the Milky Way will pass near regions of Andromeda where gravity tugs them onto new paths. Some may be thrown outward into long trails of stars stretching far into space. Others may be pulled inward. Some might end up in unstable orbits for a time before settling into new, stable paths. But none of these changes involve stars physically hitting one another. It's a reshaping, not a smashing. The reason gravity shapes orbits without causing collisions has to do with the way stars move. Stars travel through galaxies at high speeds. The Sun, for example, moves around the centre of the Milky Way at about 220 kilometers per second. Other stars move at similar or sometimes even faster velocities. These high speeds mean that even when two stars pass relatively close to each other, they don't have time to pull each other into a collision. The gravitational pull between them is too weak compared to their momentum. They pass by each other, curve their paths slightly, and then continue on. The only way for stars to collide would be for them to approach extremely slowly and directly, with their paths lined up toward one another perfectly. But the odds of that happening inside a galaxy, even during a merger, are extraordinarily small. This idea becomes easier to grasp when you imagine how galaxies behave on large scales. The stars inside them don't simply drift randomly. They follow organized patterns shaped by the galaxy's rotation and gravitational balance. When one galaxy passes through another, those patterns become distorted, but they don't turn into chaotic swarms. The stars continue moving according to the new gravitational landscape, not toward individual targets. The motions are collective, not personal. It's like watching a flock of birds shift direction when a wind gust hits. The birds adjust their paths as a group, but they don't start crashing into one another simply because the wind is strong. They respond to the change collectively, maintaining space between them. Another factor that keeps stars apart is their relative sizes. Even though stars are massive, they occupy very small volumes compared to the space around them. The Sun, for instance, is huge compared to Earth, but minuscule compared to the vast distances of the galaxy. For a physical collision to occur, two stars would need to pass within a tiny fraction of their separation distance. It's like two insects flying through a large warehouse. Even if the warehouse were filled with millions of insects, the odds of two hitting each other at any specific moment would still be low. Scale matters. In a galaxy, the scale is so enormous that collisions remain improbable. Even during the final stages of a merger, when the central regions of the galaxies are mixing, the stars remain far enough apart that collisions are negligible. The only part of the collision where models predict significant changes in density is near the very centre of the merging galaxies, where the supermassive black holes reside. But even there, stars are not densely packed enough to collide frequently. The black holes themselves might eventually merge, but the stars around them continue orbiting in complex patterns without crashing into each other. The rarity of star collisions is also reflected in the stability of planetary systems. If stars frequently collided during galactic encounters, planets would be destroyed regularly. Solar systems like ours would be highly vulnerable, but the survival of old stars and planets across billions of years shows that the galaxy is a calm enough environment that such destructive events are uncommon. Even when galaxies pass through each other, solar systems remain intact. The Earth has circled the Sun for 4.5 billion years without any sign of nearby collisions. Other systems have done the same. This long-term stability is evidence that the galaxy is spacious enough to allow stars and planets to exist peacefully for billions of years. This deep emptiness between stars is one of the reasons the universe feels simultaneously enormous and quiet. For all its dazzling displays of light and motion, most of the cosmos is calm on the scale of individual stars. The light we see from galaxies represents only a tiny fraction of what's out there. It illuminates the sky, but the space between those lights is so open that galaxies can drift into one another without ever producing the kind of catastrophic impacts we might expect. This is why the Milky Way and Andromeda merging is not a danger to stars inside them. Instead, it's a slow restructuring that preserves the stars themselves while rearranging their paths. When two galaxies begin to influence each other during a merger, one of the earliest and most recognizable features that emerges is the formation of long, delicate streams of stars that stretch outward from the edges of each system. These structures, known as tidal tails and the cosmic ribbons that extend from them, are among the most striking signatures of galactic interactions. They look almost like trails of light painted across space, curving and twisting as they follow the changing gravitational landscape. They're not physical tails in any solid sense. They're vast, extended paths made of stars, clusters, and gas drifting in new directions because of the redistributing pull between galaxies. Understanding how these structures form requires imagining not just the motions of stars, but the way gravity shapes entire systems when two massive objects move close enough to influence each other. When the Milky Way and Andromeda begin their long encounter, the first part of them that will react to this changing gravitational field is their outskirts. The stars in the outer regions are less tightly bound to the centres of their galaxies because they're farther from the majority of the mass. This means they're more sensitive to outside influences. If a distant galaxy passes near enough, the outer stars start to feel a secondary gravitational tug. They're still bound to their home galaxy, but the pull is not as strong as it is for stars closer to the core. So when Andromeda's gravitational field begins to overlap with the Milky Way's, the stars near the edges are the ones that respond first, bending their paths gradually as they feel this new force. This bending of orbits creates what astronomers call tidal forces. Tidal forces exist whenever gravity pulls more strongly on one side of an object than the other. On Earth, tides in the ocean come from the Moon pulling more on the nearest side of the planet than on the far side. The difference is tiny, but noticeable. In galaxies, the same principle applies, except on a much larger and more complex scale. When the Milky Way approaches Andromeda, the side of the Milky Way facing Andromeda feels a slightly stronger pull than the side facing away. The same happens in reverse for Andromeda. Over millions of years, these differences stretch the galaxy slightly in the direction of the gravitational pull. The stretching is not violent. It's a slow, patient expansion of the outer regions, where stars begin to drift outward into long arcs. These arcs form because the stars follow the new paths dictated by gravity. They aren't pulled apart like a rope being stretched. Instead, they move along their natural orbits, which slowly transform as the gravitational environment evolves. If you imagine a star moving in a circular orbit around the Milky Way's centre, that path becomes elongated once Andromeda approaches closely enough. The star's orbit becomes more elliptical. Over time, the orbit stretches even further until the star travels so far from its original position that it becomes part of a tidal tail. This entire process can unfold smoothly over hundreds of millions of years without any sudden jerking or shifting. The star doesn't even notice anything dramatic happening. It simply follows the gravitational path available to it. Tidal tails are among the most dramatic visual effects of galaxy interactions because they can stretch to enormous distances. In some observed galaxy mergers, these tails extend hundreds of thousands of light years from the centre, far beyond the size of the original galaxies. They may form symmetrical shapes, like two sweeping arcs that mirror each other, or asymmetrical winding trails that curve in complex patterns. The exact shape depends on how the galaxies meet, whether they pass each other closely, strike at an angle, or approach head-on. The Milky Way and Andromeda are expected to produce large tidal tails during their first close pass-through, forming enormous streams of stars that drift outward into space. Within these tidal tails, the density of stars is generally lower than in the main body of the galaxy, but they're still home to enormous numbers of stars. Some of these stars are old, having been pulled from the outskirts of their original galaxies. Others are newly formed. When gas clouds inside the galaxies are stretched into these tails, they can collapse under their own gravity and give birth to new stars. These newborn stars often form in clusters, glowing brightly and making parts of the tidal tail visible even across great distances. In images of interacting galaxies taken by powerful telescopes, these bright knots appear like pearls shining along the length of a cosmic ribbon. The creation of these cosmic ribbons is not simply a matter of stretching. Gravity shapes them in intricate ways. As the galaxies move, the tidal forces change direction. This changing pull causes the streams of stars to curve and twist. The motion of the galaxies themselves also plays a role. Galaxies rotate, so stars have built-in momentum that influences the shape of the tail. If Andromeda approaches the Milky Way at a particular angle, the rotation of both galaxies will create spiraling patterns in the drawn-out material. This is why tidal tails often have curved structures with graceful bends rather than straight lines. They trace the combined motion of stars influenced by two massive gravitational fields that are themselves in motion. As tidal tails grow, they become temporary bridges of material between the merging galaxies. These bridges are not solid, but they serve as highways where some stars may travel from one galaxy into the other. Others may drift into intergalactic space, forming isolated streams of stars that remain separate from both galaxies for long periods. These wandering stars can persist long after the merger is completed, functioning almost like memories of the encounter. In some observed mergers, these extended streams remain visible billions of years after the galaxies have finished settling into their final shape. In the early stages of the Milky Way-Andromeda encounter, the tidal tails will begin forming before either galaxy fully overlaps. The outskirts will stretch first. Then, as the galaxies pass through each other, the tails will lengthen dramatically. Along these tails, stars will be found in loosely organized collections, sometimes forming faint arcs that curve around the merging system. These arcs are not static. They drift, rotate, and slowly disperse over time. Many of the stars in these tails will eventually fall back toward the merging galaxy, becoming part of its outer regions. Others will escape entirely, drifting into intergalactic space where they will wander for billions of years. This process is not unique to the Milky Way and Andromeda. Astronomers have observed tidal tails in numerous other mergers across the universe. These structures are common and serve as evidence of past encounters. In some cases, tidal tails can be so prominent that they will reveal how the galaxies interacted long after the main body of the resulting galaxy is settled. They act like footprints, showing where the two galaxies passed closest to each other and how their motions were oriented. By studying these tails, astronomers can reconstruct the history of a merger in remarkable detail. One particularly interesting feature of tidal tails is the presence of what are sometimes called tidal dwarf galaxies. These are small, dense regions within a tail where gas collapses and forms stars. Although they're made from material pulled out of the original galaxies, they can grow dense enough to become small galaxies in their own right. They orbit the merging system and may survive long after the rest of the tidal tail has dissipated. If the Milky Way and Andromeda's merger creates these dense regions, they may become tiny companions to the final merged galaxy, drifting around its outskirts. Inside the tidal tails, the motion of stars is shaped not only by the gravitational forces of the two merging galaxies, but also by the internal motions of the stars themselves. Stars have their own velocities. They don't simply travel along the tidal tail like beads on a string. They move within the tail, sometimes drifting forward or backward, sometimes spreading out as the tail disperses. This motion helps determine how long the tail remains visible. The more dispersal that occurs, the more the tail gradually fades into the background, blending with other stars in the outer regions of the merged system. The gas inside the tidal tails behaves differently from the stars. Gas is more easily compressed, and as it is stretched into long filaments, it may cool and collapse to form new stars. However, it can also be stripped away or heated by the energetic environments of the merging galaxies. Regions where the gas becomes dense enough to collapse can produce star-forming knots along the length of the tail. These knots shine brightly in ultraviolet light because young stars emit large amounts of high-energy radiation. Observations of other galaxies show that these bright knots sometimes appear at intervals along the tidal tail, almost like beads evenly spaced on a long thread. The development of tidal tails also hints at the future shape of the merged galaxies. As material is drawn outward, the central regions become more extended. Once the tails begin to fall back, they help build up the outer halo of the final galaxy. The halo is a large, diffuse region around galaxies where stars are more scattered and move in more random orbits. The merging of tails into this halo contributes to its growth. So when the Milky Way and Andromeda's tails eventually disperse, many of the stars will become part of the outer halo of the new galaxy that forms after the merger. These features play an important role in helping the galaxies eventually settle into their final form. Tidal tails redistribute mass. They move stars outward. They create new structures. They help dissipate energy by spreading material across larger volumes. All of this shapes how the galaxies blend together. The more mass that redistributes, the more the system can lose the orderly rotation that once defined its spiral shape. Over time, as the tails disperse and stars fall back into the system, the galaxy becomes smoother and rounder. This is part of the slow transformation from two spirals into a larger, more elliptical galaxy. While this process may sound complex, it unfolds naturally according to gravity. Nothing about it is chaotic in the sense of immediate disorder. The patterns that form are predictable when viewed over long periods. Every star follows the gravitational field, and the field evolves according to the mass distribution of the galaxies. The result is a series of structures that trace the motion of the entire system. These tidal tails, cosmic ribbons, and elongated arcs all reflect the ongoing interaction between the galaxies. For an observer living on a planet inside the merging system, the formation of these tails would not be noticeable in real time. The process is so slow that even across millions of years the changes would be subtle. Only through astronomical observations comparing snapshots across deep time would the tails become visible. But if intelligent life existed billions of years in the future, they might see long, faint streams of stars arcing across the sky, marking the way their galaxy once met another. These trails would be faint reminders of the dramatic reshaping that occurred over spans of time far too large for individual lifetimes to hold. As the Milky Way and Andromeda move deeper into their long interaction, the gentle stretching of their outer regions begins giving way to changes that run far beneath the visible structure. The tidal tails that drift outward trace the delicate outer response, but inside the galaxies something far more transformative begins. Gas clouds that once drifted quietly along stable orbits start entering regions where gravity acts in new, uneven ways. These clouds are the raw material for star formation. They are massive reservoirs of hydrogen and helium, drifting as loose structures for millions of years until the right conditions allow them to collapse. When galaxies interact, those conditions become far easier to achieve. What follows is not an explosion or a moment of violent upheaval, but a long and productive era where entire regions glow with new light. These periods are known as starburst epochs, times when the galaxy forms stars far more rapidly than usual. The Milky Way today forms stars at a moderate and steady pace. Some stars ignite in the dense regions of the spiral arms, where gas compresses gently as the galaxy rotates. New stars flicker into existence, but the rate is calm and controlled. Andromeda too formed stars at a rate that is neither slow nor fast by galactic standards. But when two galaxies merge, this peaceful balance shifts, because the clouds of gas within them begin to encounter forces that disturb their long-standing equilibrium. Gas does not behave like stars. While stars pass through each other unaffected, gas clouds collide, compress and heat up. They can be pushed, squeezed and reshaped by the changing gravitational environment. When two galaxies overlap, the gas inside them can be driven into new regions, where it is forced together more strongly than at any time in their normal evolution. This process unfolds slowly compared to a human lifetime, but quickly in galactic terms. When the Milky Way and Andromeda begin to pass through each other, the gas clouds inside them start encountering turbulence. The gravitational field becomes uneven. Regions that were once quiet now feel shifting forces. Clouds begin to drift into areas where the pressure around them increases. If two gas clouds pass near each other, their interaction can create ripples that travel through the gas, pushing it inward. These ripples can trigger the collapse of these enormous clouds. When a cloud collapses under its own gravity, it doesn't form just one star. It forms many, hundreds, thousands, sometimes tens of thousands. This is the beginning of a starburst epoch. It's not a single burst, but instead a long phase during which star formation becomes dramatically more intense. Instead of forming stars slowly and steadily, the merging galaxies may give rise to so many new stars that the galaxies brighten significantly in certain regions. These star-forming knots can outshine the rest of the galaxy temporarily, because the stars born during these bursts are often massive. Massive stars burn brightly and live short lives, sometimes only a few million years. But during their brief existence, they radiate huge amounts of light, heating the gas around them and illuminating the merging system. Starburst regions are among the brightest features of galaxy mergers. Observations of interacting galaxies across the universe reveal that these star-forming regions often appear as glowing clusters scattered along the paths where the galaxies overlap. Some appear as dense, compact clusters. Others form elongated clouds that glow in ultraviolet and infrared light, depending on the stage of their development. They often become the most striking features in images, forming arcs, knots, or large patches of brightness. If you were to observe the Milky Way and Andromeda's merger from a distance, these bright regions might stand out even more than the tidal tails themselves. The reason these starbursts occur so readily during a merger has to do with how gas behaves. In a calm galaxy, gas clouds are often supported by pressure, turbulence, or magnetic fields. They drift along, occasionally forming stars where the conditions are just right. But the gravitational disturbances caused by a merger disrupt this delicate balance. Suddenly, gas clouds experience forces from multiple directions. Some are compressed by tidal forces, others are shoved into regions with higher density. Some clouds might even be driven deep into the merging core where gravity is strongest. These movements create layers of compression that make it easier for the gas to condense. Once this process begins, it spreads. One collapsing cloud can trigger others nearby by sending shockwaves through the surrounding gas. The collapse becomes contagious, spreading across large regions of the galaxy. During these epochs, the galaxies may produce stars at rates many times higher than their normal pace. Instead of forming a few stars each year, they may form dozens or even hundreds annually. Over the course of the entire merger, billions of new stars may be born. These stars add their light to the evolving system, creating stunning regions of brightness that mark the primary sites of activity during the collision. While the tidal tails trace the outer encounter, the starburst regions illuminate the internal transformation. If you could drift through one of these starburst regions, the view would feel dramatically different from the quiet suburban regions of the Milky Way where the sun resides. Space would still be mostly empty, as it always is, but the gas clouds would be denser, warmer, and more chaotic. Newly formed stars would shine intensely, many of them larger and brighter than the sun by orders of magnitude. Young clusters might appear as tightly packed groups of stars, glowing blue or white due to their high temperatures, these clusters form because many stars emerge from the same collapsing gas cloud, creating associations that can last for hundreds of millions of years before slowly dispersing. Massive stars formed during starburst epochs play a crucial role in shaping their surroundings. Their radiation, stellar winds, and eventual supernovae can further compress or disrupt nearby gas. This feedback creates a cycle where one generation of massive stars influences the next. In some cases, feedback from massive stars can even halt star formation locally for a time by blowing gas outward. But on galactic scales, the overall burst continues, moving from region to region as the merger progresses. It is not a single unified event, but a patchwork of activity spread across millions of light years. As the Milky Way and Andromeda enter their later stages of merging, the frequency and intensity of starbursts may increase in the central regions. The core becomes denser as stars and gas fall inward. The gravity of the combined system draws material toward the center, where conditions become ripe for large bursts of star formation. These central starbursts can be so energetic that they form compact clusters containing millions of stars. Some of these clusters may survive for billions of years, becoming globular clusters in the final merged galaxy. Others may disperse more quickly, adding their stars to the central bulge. The merging of gas into the central region can also feed the galaxy's supermassive black holes. As gas funnels inward, the black holes may begin consuming some of this material. When black holes feed, they can emit jets and radiation that affect the surrounding region. This activity may temporarily suppress star formation in the innermost areas, but the overall starburst activity across the galaxy continues. The central regions become a complicated environment where star formation, black hole activity, and gravitational turbulence all interact. For any observers hypothetical enough to exist during the merger, the night sky would slowly fill with new patterns of light. Over millions of years, the starburst regions might create patches of brightness that were not present before. New clusters might become visible as tight knots of stars. Some may form shapes or patterns that shift only gradually as the galaxy evolves. The sky would become subtly more crowded with bright young stars, especially in regions where bursts are most active. Even though everything would still happen slowly, the cumulative effect over long spans of time would reshape the visible structure of the sky. Starburst epochs also play a major role in determining how the final merged galaxy will look. The new stars formed during these bursts add mass to the central regions, helping the galaxy grow rounder and denser. The bursts also contribute to the transformation of spiral galaxies into elliptical ones. Spirals have ordered rotation. Ellipticals have more random star orbits. When two spirals merge, the starbursts help redistribute gas and build up the central bulge, which contributes to the rounder shape. Once the gas is used up or heated by feedback processes, the rate of star formation slows dramatically. The final galaxy becomes dominated by older stars, with fewer new ones forming. This transition marks the end of the starburst era and the beginning of a quieter, more settled phase. These starburst periods are often the most visible sign that a merger is actively reshaping a galaxy from the inside. While tidal tales trace the stretching from the outside, starburst regions reveal the compression occurring deep within. Both of these processes are responses to the same gravitational interaction, but they manifest in very different ways. One creates long, elegant structures drifting outward. The other ignites new stars in dense, glowing patches. Together they define the intermediate stages of galactic evolution during a merger. When thinking about a collision between two galaxies as large as the Milky Way and Andromeda, it's natural to wonder what becomes of our own Sun in the middle of such an enormous rearrangement. The question feels personal in a way that the wider cosmic story doesn't. Tidal tales and bursts of new stars unfold on scales that are difficult to hold in mind, but the Sun is familiar. It is the center of our experience, the source of every warm day and every season, the anchor that keeps the solar system moving in its steady pattern. Imagining the Sun drifting through a changing galaxy makes the whole event feel closer, more relatable. But the fate of the Sun during this merger isn't a story of destruction or dramatic upheaval. Instead, it's another example of how surprisingly gentle the encounter will be, even though it reshapes two entire galaxies. The Sun, like every star, is bound to the gravitational field of the Milky Way. It moves around the galactic centre at a speed that feels incredibly fast in human terms, but very natural on a cosmic scale. One orbit around the Milky Way takes the Sun roughly 230 million years. During that time, the Sun doesn't follow a perfect path. It bobs slightly above and below the galactic plane, drifts a little inward or outward, and moves through regions where stars are slightly denser or more spread out. But these changes are small compared to the vastness of the galaxy. The Sun's orbit is stable enough that life on Earth has been able to evolve quietly for billions of years. As the merger begins, this stability doesn't suddenly vanish. The gravitational influence of Andromeda grows slowly, just as the entire collision unfolds slowly. When Andromeda's outer regions start affecting the Milky Way, the Sun feels that influence as a subtle change in the direction and strength of the galaxy's gravitational pull. But these changes are far too small to disrupt the solar system. The Sun remains the dominant source of gravity for all the planets. Nothing in the merging galaxies is strong enough or close enough to pull Earth or the other planets away from their orbits. From the perspective of someone living on Earth, the solar system would continue moving as it always has. What does begin to change slowly and quietly is the Sun's position within the larger galaxy. As the gravitational fields of the Milky Way and Andromeda begin blending, the orbit of the Sun shifts. It may drift outward or inward depending on the exact distribution of mass during each stage of the merger. Over millions of years, its path might stretch or tilt, but it remains bound to the merging system. The Sun doesn't fall into one galaxy or the other. It becomes part of the combined gravitational environment, just like every other star. This process is smooth because the Sun is small compared to the influence of the galaxy. Even though the Sun is massive to us, it is a tiny component of the Milky Way. Changes to the shape of the galaxy influence the Sun the way a gentle slope influences a rolling ball. The ball continues moving smoothly along the landscape. It doesn't bounce or fly upward. It simply shifts its motion as the ground beneath it changes. The Sun follows these changing gravitational contours naturally, drifting along without encountering sudden disruptions. One of the important factors that protects the Sun during the merger is the extreme emptiness of the galaxy. Even though the Milky Way contains hundreds of billions of stars, the distances between them are so vast that direct interactions are rare. The chances of the Sun passing too close to another star during the merger are extraordinarily small. Most stars will continue drifting through the emerging system, without ever coming close enough to disturb each other's planetary systems. This means the solar system is not at risk of being torn apart, disrupted or flung out of the galaxy because of a nearby star passing too close. The Sun remains relatively isolated, even in a galaxy filled with stars. As the merger progresses and the Sun moves through regions where star formation is more active, it may pass near areas where new clusters are forming. These clusters would appear as bright patches in the sky, but they would remain far enough away that the solar system would not be affected by their radiation or gravitational influence. The Sun might pass near some of the tidal structures, or move through regions where the density of stars is slightly higher, but these differences are small on the scale of the solar system. They would not alter the orbits of planets or cause any noticeable disturbances. Over the course of the merger, the Sun's orbit will likely become more irregular. Instead of following a mostly circular path around the centre of the Milky Way, it may begin to move in a more elliptical or tilted orbit around the centre of the merged galaxy. This kind of shift is normal during mergers. Stars are redistributed across the forming system, and many of them end up on new paths. The Sun may find itself in a region farther from the galactic centre than where it started. It might drift outward into the halo, or move toward the inner regions depending on the overall flow of mass during the merger. But these changes unfold slowly enough that nothing about the solar system's internal balance is affected. One of the most striking changes for any distant observer would be the appearance of the night sky. Today, the Milky Way appears as a faint band of light stretching across the sky. Over millions of years, as Andromeda approaches, that faint glow would gradually change shape. The Andromeda galaxy, now a small blurry patch of light, would grow larger and more detailed. At first, it would appear as a slightly larger smudge. Then, over hundreds of thousands of years, it would stretch into a visible spiral. Over millions of years, it would fill a significant portion of the sky. This change would be far too slow for a single lifetime to perceive, but over cosmic timescales, it would transform the night sky completely. As the galaxies begin overlapping, the sky would take on shapes never seen before. Streams of stars from tidal tails might appear as faint arcs. New star-forming regions might glow as bright patches. Eventually, the sky would look unlike any sky that humanity has ever known. The merger would create a sky filled with more structure, light, and complexity than the present one. The shapes of the constellations would shift slowly, not because the stars are changing dramatically, but because their positions relative to Earth drift over millions of years. The familiar patterns would warp and rearrange. New patterns would form. All of this would be gentle and gradual, part of the ongoing transformation of the galaxy. Throughout the entire process, the Sun continues aging. Long before the merger completes, the Sun will have moved far into the later stages of its life. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin expanding into a red giant. This transformation is independent of the merger. Whether or not Andromeda ever approached, the Sun would still follow this life cycle. The red giant phase will change the solar system dramatically, potentially consuming the inner planets and altering the conditions around the outer planets. The Earth, if it still exists, might no longer be habitable by the time the Sun reaches this stage. Any changes in the galaxy caused by the merger are secondary compared to the evolutionary path of the Sun itself. This means that the Sun's own life will have a more significant impact on the solar system than the merging of two galaxies. The galaxy will be shifting around the Sun, but these changes will be slow and gentle compared to the Sun's internal evolution. The fate of the Earth and the planets depends far more on the Sun's aging than on the merger. The galaxy's transformation is the backdrop, not the driving force of what happens to the solar system. If any hypothetical observers existed during the final phases of the merger, they would see the Sun becoming part of the newly formed galaxy, often called Milkdromeda by astronomers. In this future galaxy, the Sun would continue orbiting along whatever path it has settled into. Eventually, after the Sun exhausts its fuel completely, it will shed its outer layers and become a white dwarf. This white dwarf would drift quietly through the merged galaxy, shining faintly for billions of years more. It would be just one of many stars that remain as long-lived remnants of the original Milky Way. The Sun's journey through the merger illustrates the way the universe balances vastness with stability. Even though two enormous galaxies collide and reshape the structure around it, the Sun remains intact, the planets continue orbiting, and the solar system survives without any catastrophic changes. The galaxy can shift its shape dramatically without disrupting the small-scale systems inside it. This stability is one of the most reassuring parts of understanding how mergers work. When imagining how the Earth's sky will change as the Milky Way and Andromeda drift into one another, the mind naturally jumps to sudden shifts, to dramatic displays that light up the horizon, to something unmistakably noticeable in the span of an ordinary life. But the sky almost never behaves that way. The sky's a patient canvas, one that updates itself in increments so small you can only detect them if you step far enough back in time. Even the stars that trace their familiar constellations across our nights are not fixed. They move, slowly but constantly, shifting in directions that only become visible across thousands of generations. The merger of two galaxies is no exception to this pace. The sky will transform, but in a way that is measured not in centuries or millennia, but in spans so vast that the sky becomes a record of time itself. The first changes would begin long before the galaxies actually overlap. Andromeda, which today appears as a faint smudge in dark skies, will gradually grow larger. Its light will spread across a wider patch of the sky as the galaxy approaches. The change would be too subtle to notice in a human lifetime, but over tens of thousands of years, Andromeda would shift from being an object that requires dark, clear skies to be visible to becoming a prominent, unmistakable feature. At some point, it would no longer look like a faint cloud, it would begin revealing structure. The shape of its spiral arms might become faintly detectable to the eye. The bright central region would expand. If anyone were around to see it, they might describe the change as the slow blooming of a distant light. As the galaxy continues to approach over millions of years, its spiral pattern would become clearer. Its arms would stretch across a larger portion of the sky, creating a shape unlike anything visible today. The Milky Way's band would still be present, but Andromeda would be rising to rival it. The two structures would take up separate regions of the sky, each with its own patterns of light. The familiar constellations would continue shifting, but now a vast hazy spiral would sit in the background, slowly growing as the merger draws closer. The widening of Andromeda's appearance would not alter the rhythm of nights or the rise and fall of the moon. The changes would be purely visual, slow enough that each generation would inherit a sky slightly altered from the one before. The idea of a static sky would become less accurate across deep time. Instead of a single band of light stretching across the night, the sky would contain two. Andromeda's glow would add a second galactic presence, creating a sky that looked layered in ways impossible to imagine today. Over time, the approach would continue until Andromeda's disk spanned a large portion of the night sky. It might cover an area 30 or 40 times larger than the moon. It would be too faint to cast shadows, but bright enough to paint a permanent glow overhead. Anyone who managed to witness even a small fraction of this slow transformation would see the galactic features grow sharper. Dark lanes of dust might become visible. Clusters of bright stars in Andromeda's spiral arms might stand out clearly. The sight would be breathtaking but gentle, a change that unfolds not through sudden appearances but through the accumulation of subtle, nightly shifts over vast spans of time. As the galaxies drift closer and the gravitational interaction becomes stronger, the sky would begin to reveal signs of the forming tidal tails. These would not appear all at once. They would first emerge as faint arcs or diagonal streaks of light, subtle enough to blend with the stars at first. Over millions of years, these arcs would stretch farther across the sky, gently curving into long, faint trails. They would resemble ghostly ribbons sweeping across the horizon. If the Earth is still home to observers during this stage, they would not see stars streaking across the sky or notice sudden twists in the galactic structures. Instead, they would see the slow, elegant unfurling of new shapes, each one appearing as if it had always been there. Eventually, the sky would become layered with features from both galaxies. The Milky Way's band would no longer be the dominant structure. Andromeda's light would become comparable, if not brighter, depending on where the Sun ends up in its evolving orbit. The sky would contain overlapping arcs, glowing patches, and swirling structures that seem to fade into one another. It would be a sky full of blended shapes, betraying the gravitational partnership of two galaxies in the midst of transformation. During the first close approach, when the galaxies begin to pass through each other, the sky would shift into something that no human alive today has ever seen. But even then, the changes happen far too slowly to perceive directly. Instead, over hundreds of thousands of years, the stars overhead would begin spreading into new patterns. Some regions might grow brighter as pockets of star formation ignite. Others might darken as dust clouds drift into the line of sight. New shapes would emerge, and old shapes would fade. The constellations, which have been used for navigation and storytelling for thousands of years, would eventually become unrecognizable. Orion, Cassiopeia, the Big Dipper, these would distort as their stars drift along their own long arcs around the galaxy. But now the background against which they move would include entire arms of a neighbouring galaxy. Constellations that once seemed to sit against a dark canvas would appear against a luminous swirl of stars. The idea of constellations would lose its meaning entirely. There would be no obvious boundaries, no clear shapes, because the sky would contain too much structure to isolate simple patterns. The night would resemble an enormous cosmic mural instead of a collection of familiar points. As the merger progresses further, the galaxies would begin to overlap visually. The Milky Way's central bulge would appear distorted. Andromeda's bright core would drift across the sky, eventually occupying a region close enough to blur with the Milky Way's own central light. Instead of two spirals, the sky would begin to show the early signatures of a single blended structure. The merging cores would create a bright region that spans a large portion of the horizon. It wouldn't be blinding, but it would be visibly luminous, like a gentle glow spread across a wide area of the night sky. Dust lanes, those dark branching regions visible in many spiral galaxies, might become prominent features overhead. In the merging system, dust clouds could be drawn into new patterns, creating dark patches and streaks silhouetted against the brighter background. The sky wouldn't be uniformly bright. It would be a mosaic of luminous regions and soft shadows. Starburst regions, ignited by the compression of gas during the merger, would contribute their own vibrant patches of light. These regions are extremely bright, especially in ultraviolet wavelengths. To the eye, they might appear as unusually bright clusters, dense pockets of young stars glowing with an intensity unmatched by the older stars around them. Over millions of years, these regions might shift location as the merger evolves, moving across the sky like drifting islands of light. As time progresses and the galaxies reach the middle stages of merging, the sky would grow even more complex. Instead of two spirals, the combined system would begin looking like a distorted, irregular cloud of stars. The cores might be indistinguishable from each other. The glow from the merging centers would spread across the sky, covering a region large enough to be visible even in daylight as a faint, diffuse brightness, though not strongly enough to overshadow the sun. At night, it would dominate everything. During the late stages of the merger, when the galaxies have passed through each other multiple times, the sky would settle into a new pattern. The tidal tails would fade, the arcs and ribbons would disperse. What remained would be the long, slow coalescence into a single galaxy. The sky would reflect this change by gradually smoothing out. Instead of the pronounced spiral patterns of the Milky Way, the night sky would show a more amorphous glow. The central region of the new galaxy would look larger and rounder. The disk would lose its distinct shape. Over time, the sky would transition into something softer, with more diffuse light spread evenly across a wide area. Through all this, the sun would continue moving along its orbit, carrying the solar system through different regions of the forming galaxy. Depending on its path, the sun might pass through areas with more dense star formation, or drift through quieter zones. In either case, the sky would continue reflecting the motion. Subtle changes would occur as the sun's position relative to the new galactic core shifts. The sky might brighten or dim slightly, depending on the density of stars in the surrounding region. Eventually, when the galaxies have merged fully into a single system, the sky would look drastically different from the one humanity was born under. The band of the Milky Way would be gone. The concept of a single clear structure stretched across the sky would no longer apply. Instead, the night would be filled with a more uniform glow from the vast, rounded distribution of stars in the elliptical-like galaxy that emerges. There would still be bright clusters, dark dust lanes, and patches of star formation, but the overall structure would be smoother. The sky would appear filled with stars in all directions, not concentrated along a single band. For any hypothetical observers, this new galaxy would feel immense and surrounding. Instead of a sky that feels like it has a decorated ceiling along one direction, the entire dome above would be filled with a more even density of stars. The familiar sense of direction provided by the Milky Way's band would be gone. Instead, the sky would be a more continuous sweep of lights, stretching uniformly in all directions. It would feel both larger and more intimate, because the distribution of stars would no longer highlight a single plane. Even after the merger, the sky would continue to evolve. The new galaxy, often referred to as Andromeda, would slowly settle into its final shape. The stars would find new orbits. The central regions would grow denser. The Sun, whether still active or long since transformed into a white dwarf, would complete orbit after orbit in this new structure, and the sky would keep shifting generation after generation, reflecting the gentle, constant motion of everything within the galaxy. When thinking about the Milky Way and Andromeda drifting toward one another across millions of years, the focus often lands on the stars, the tidal tails, and the changing sky. These are the parts that feel tangible, the pieces we can imagine, points of light, arcs of glowing material, the slow turning of the night. But at the centres of these galaxies lie something far more compact and yet far more influential than any single star. The Milky Way has a supermassive black hole at its core, a dense object millions of times the mass of the Sun. Andromeda has one as well, even larger. These central black holes sit quietly in the heart of their galaxies, shaping the orbits of nearby stars and anchoring the innermost regions. They do not dominate the galaxy as a whole, but they are unmistakably important pieces of the larger structure. When two galaxies merge, their supermassive black holes eventually meet, drawn together by the combined gravity of the new system. It is tempting to imagine that when two objects with such enormous mass encounter each other, the process is chaotic or destructive, something like an explosion or a sudden spiral inward. But as with everything else about the merger, the reality is slow. It is measured. It unfolds through subtle shifts in the motion of stars and gas over extraordinary lengths of time. The merging of two supermassive black holes is not a moment. It is an era, one that takes place long after the galaxies themselves have intertwined. Before these black holes can begin approaching each other closely, the galaxies first need to reach a stage where their central regions physically overlap. For most of the early merger, the black holes remain far apart, each continuing to sit at the centre of its respective stellar structure. Even when the galaxies' outer disks pass through one another, their cores remain distinct. They carry their black holes with them, much the way two large crowds might walk through each other without the people in the centre ever bumping. The black holes remain insulated by the stars and gas in their immediate neighbourhoods. The gravitational influence of each black hole is strong, but only over a limited region. Stars nearest to each black hole continue to orbit it, giving each galaxy's core enough stability to persist through the early phases of the merger. As the galaxies interpenetrate multiple times, their central regions begin to lose the clean boundaries that once separated them. The stars near the cores are pulled into new orbits by the combined gravitational field. Gas falls inward from both galaxies, feeding the central regions with material. Gradually, the two black holes become part of a single, larger gravitational environment. They don't fall directly toward each other at first. Instead, they drift, carried by the combined structure of the merger. The gravitational potential of the merging galaxies slowly reshapes itself, becoming shallower in some areas and deeper in others. This slow rearrangement pulls both black holes closer to the centre of the forming galaxy. Once the black holes move into the same general region, they begin influencing one another more strongly. However, they are not yet close enough for their gravity to bind them together. Instead, they begin sinking toward the very centre of the merged galaxy through a process known as dynamical friction. This process is not friction in the everyday sense. Nothing is physically rubbing against anything else. Instead, the black holes move through fields of stars, gas, and dark matter, and these particles respond subtly to their presence. As a black hole passes through a dense region, it gravitationally perturbs the surrounding stars and gas, creating a slight overdensity behind it. This overdensity tugs on the black hole, stealing a tiny amount of its momentum. Over millions of years, this effect causes the black hole to lose energy and move inward, sinking toward the center as the surrounding material shifts in response. This sinking happens to both black holes. Each begins spiraling gradually toward the center of the combined galaxy, carried inward by the quiet but persistent influence of dynamical friction. The process is slow because the black holes are moving through enormous regions filled with stars that are themselves moving in various directions. It's not a straight path, but a wandering one, shaped by the distribution of stars and gas in the merging core. Eventually, after millions of years of this process, the black holes come close enough to each other that their gravitational pull begins to dominate the region around them. At this point, the black holes form what astronomers call a binary system. They begin orbiting one another, though not in a neat circle the way planets orbit stars. Their initial orbits may be elongated and chaotic. They may pass close sometimes and drift farther apart at others. Stars passing near them can be slingshotted away at high speeds. Gas drifting inward can feed one or both black holes, sending jets of radiation outward. The binary black hole phase is one of the most important stages of the merger, because it sets the stage for the final coalescence. The forces acting on this binary system are complex. The surrounding stars play a significant role. When a star passes close to the binary, it can extract energy from the system, causing the black holes to move a little closer. Over time, many such encounters occur. Stars are flung outward, sometimes even ejected from the galaxy entirely. Each encounter removes a small amount of energy from the binary. This loss of energy is what gradually tightens the orbit, making the black holes spiral slowly inward. Gas can also influence the binary. If clouds of gas fall toward the center, they can interact with the black holes in various ways. Gas may form a disk around one or both black holes. It may be heated to extreme temperatures and emit bright radiation. It may be consumed by the black holes, increasing their mass. These interactions can extract energy from the binary system, helping bring the black holes closer. The balance between stars and gas determines how quickly this stage unfolds. In some galaxies, the gas is plentiful, and the black holes merge relatively quickly. In others, the gas is sparse, and the black holes may remain in a binary configuration for long periods. When the black holes get close enough, the process enters its final phase. At this stage, gravitational radiation becomes the dominant way for the system to lose energy. Gravitational waves are ripples in the fabric of space-time itself, produced whenever massive objects accelerate. When two supermassive black holes orbit each other closely, the curvature of space-time around them shifts rapidly enough to create these waves. The waves carry energy away from the system, causing the black holes to spiral inward faster. This phase accelerates the merger, shortening the timescale from millions of years to something much shorter, though still far beyond anything perceptible on human timescales. As the black holes spiral inward, their orbital speed increases. Near the end, they move at an extraordinary fraction of the speed of light. They orbit each other rapidly, closer and closer, until the distance between them becomes so small that their horizons, the boundaries beyond which nothing can escape, overlap. When this happens, the two black holes become one. The final moment of the merger releases a tremendous burst of gravitational waves that ripple outward across the galaxy and the universe, carrying information about the masses, spins, and motions of the black holes. This burst of gravitational radiation is not something that would affect the stars or planets nearby. Gravitational waves pass through matter without causing damage. Even the dramatic waves produced by a supermassive black hole merger would be too weak to disturb anything on the scale of a solar system. But they would leave an imprint on the fabric of space-time itself. Instruments built eons in the future, if any observers existed then, might detect the waves and trace them back to the merger. After the black holes merge, the newly formed black hole settles into the centre of the galaxy. It may wobble slightly at first due to the recoil velocity created by the gravitational waves, but eventually it finds equilibrium. This new black hole contains the combined mass of both its predecessors, minus a small fraction converted into gravitational waves. It becomes the gravitational anchor of the newly formed galaxy, shaping the orbits of stars in the surrounding region. Over billions of years, this central black hole helps maintain the structure of the galaxy's core. It continues to interact with gas and stars, slowly growing larger as material falls inward. It becomes the quiet heart of the galaxy, much the way the Milky Way's black hole, Sagittarius A, is today. It is not a ravenous monster consuming everything. It is a gravitational well, a stable point around which the centre of the galaxy organises itself. The merging of two supermassive black holes is one of the most profound events in the life of a galaxy, but it happens with remarkable calm. There is no explosion, no shock wave, no destruction of surrounding stars. It is a quiet blending, governed by the laws of gravity, unfolding over periods so long that the galaxies themselves reshape multiple times before the black holes meet. The stars continue orbiting, the gas continues drifting, the galaxy continues evolving. The black holes simply do what black holes do, respond to the gravitational landscape and follow the path that physics sets before them. When this phase ends, the galaxy moves into its final era of settling. The central regions stabilise. The chaotic orbits left behind by the merger begin smoothing out. The outer regions disperse. Tidal tails dissolve into the halo. The new galaxy takes on its final shape. When two galaxies finish the long sequence of drifting, stretching, passing through one another, pulling apart and drifting back again, the final shape they settle into is not a simple blend of their original forms. The Milky Way and Andromeda, for all their majesty as spirals, cannot remain spirals once the merger has run its course. Spirals rely on order. Their arms are maintained by rotation, and the quiet rhythm of density waves travelling through the disk. When two massive disks collide and disturb each other on every level, from the delicate paths of stars to the distribution of gas and the deeper structure of dark matter, this ordered rotation dissolves. What emerges is something new, a different kind of galaxy, shaped by the long, slow ballet that preceded it. This new galaxy is often called Milkdromeda, a name that hints at its origin while recognizing it as something distinct from its parents. Milkdromeda is not a temporary phase or an unfinished structure. It is the final, settled form that comes after the merger has exhausted its chaotic motions. To understand how Milkdromeda takes shape, it helps to imagine the process not as a single moment of transformation, but as an extended era in which gravity gradually reorganizes the system from the inside out. Long before Milkdromeda earns its final shape, the two spirals have already lost the clean outlines that defined them. By this stage of the merger, the Milky Way's familiar disk has been thoroughly distorted. Its spiral arms, once stretching in elegant arcs around the core, have been twisted into irregular shapes. Andromeda's arms have suffered the same fate. These distortions start early, grow during the first close approach, and deepen each time the galaxies pass through one another. Gas clouds fall inward. Stars are flung outward. The orbits of entire populations shift, no longer aligned in the neat, largely circular patterns that supported the spiral structure. The cores of the two galaxies, with their dense star clusters and the newly merged supermassive black hole, lie near the centre of the chaos. Around them, the gravitational field has changed dramatically. Before the merger, the Milky Way's gravitational field was shaped primarily by its own mass. The same was true for Andromeda. Now, however, the combined mass creates a much deeper well. The orbits of stars in this region adjust accordingly. Stars that once followed smooth paths around their original galactic centres now find themselves responding to a new gravitational centre of mass. Their orbits tilt, stretch, or reshape entirely. Some stars come close to the core, others drift outward, joining the growing halo that surrounds the merging system. During this period, the combined galaxy does not yet have a clear identity. It may appear irregular, lopsided, or filled with distortions. The remnants of tidal tails stretch outward but are gradually losing cohesion. Many of the stars in these tails begin falling back toward the system, adding to its outer regions. The gas pulled into long filaments starts dispersing, either falling inward to feed the central regions or drifting outward, where it will eventually become too diffuse to ignite new star formation. Those early starburst regions that flared brightly during the most active stages of the merger begin to fade as their massive stars burn through their fuel quickly and end their short lives. Massive stars formed during the bursts don't last long, often only a few million years. When they die, they explode as supernovae, enriching the surrounding regions with heavy elements. These elements become part of the gas that may eventually form new generations of stars. Meanwhile, the less massive stars formed during the starburst remain, creating bright clusters that slowly disperse across the galaxy. Over hundreds of millions of years, these clusters drift apart, adding their stars to the growing, complex structure of the merged system. The motion of all these stars eventually begins to smooth out. After enough time has passed, the frantic reshuffling caused by the merger slows. Each star continues moving, of course, it never stops, but the overall distribution begins to resemble something more stable. Instead of distinct spiral arms, the galaxy develops a rounder shape. Its stars move in a variety of directions rather than maintaining a shared rotational pattern. The final result is a galaxy that resembles the large elliptical galaxies often found in the universe, though Andromeda may retain faint traces of a disk depending on how the merger plays out, and how much angular momentum the original galaxies contributed to the combined system. One of the most important influences on Andromeda's shape is the role of dark matter. Both galaxies brought enormous halos of dark matter into the merger. These halos extend far beyond the visible portions of the galaxies, shaping their motion and supporting their structure. During the merger, the dark matter halos also collide, not physically, but gravitationally. They pass through and around each other, gradually blending into a single larger halo. This halo forms the gravitational backbone of Andromeda, providing the deep well in which all the stars, gas and planets will orbit. The shape of this halo determines the final shape of the galaxy. Because the halos merge into a roughly spherical distribution, the stars eventually settle into orbits that reflect this symmetry, contributing to the rounder appearance of the new galaxy. As Andromeda takes shape, the distribution of stars becomes one of its most defining features. Instead of a thin disk with a bulge at the centre, Andromeda becomes more three-dimensional. Its stars spread out in all directions, following orbits that may be tilted, elongated, or randomly oriented. This does not mean the galaxy becomes a chaotic mess. It simply becomes a different kind of structure. The motions of stars are governed by a stable gravitational potential, so while their individual paths may differ, the overall system is balanced. Some stars, especially those ejected during the violent interactions near the merging black holes, travel on long, loose orbits that take them far from the centre. These stars contribute to a large, diffuse halo that may stretch hundreds of thousands of light-years from the core. Others remain closer, forming a dense central region with higher star density. Over time, this central region grows brighter as older stars accumulate, and new stars continue forming from the gas funneled toward the core. The fate of gas in the merged system plays a major role in shaping the final form of Andromeda. During the merger, much of the gas is driven inward by gravitational torques, twisting forces that arise when the galaxies pass through each other. This compressed gas can fuel the starburst epochs, but eventually the supply dwindles. The supernovae that erupt in starburst regions heat the surrounding gas. The feeding of the central supermassive black hole releases energy that can drive gas outward. These processes can expel or heat enough gas to slow down the rate of star formation. Over time, Milkdromeda becomes dominated by older stars, similar to many elliptical galaxies that have exhausted or heated their gas supply. This doesn't mean star formation stops completely. There will still be pockets of cold gas capable of forming stars, especially in the outskirts or in remnants of tidal tails that fall back into the galaxy, but the rate will taper off and the galaxy will transition into a quieter phase. This transition from an active, star-forming system to a more settled, older system is part of the natural evolution of mergers. As Milkdromeda matures, the orbits of stars become increasingly regular. The gravitational turbulence that characterized the early stages fades. The galaxy's shape becomes smoother and more uniform. Instead of distinct arms, the light from stars is distributed more evenly across the sky. In this settled stage, the galaxy resembles the kinds of elliptical galaxies observed in clusters, large, bright, and filled with older stars. If an observer were to drift through Milkdromeda during this era, the view would feel different from anything seen in the Milky Way. There would be no clear disk, no strong band of light marking the galactic plane. Instead, stars would fill the sky more uniformly. The density might vary depending on the observer's location, denser near the core, more diffuse in the outer regions, but the general impression would be one of surrounding brightness rather than a structured pattern. The process of forming this new identity takes billions of years, but once complete, Milkdromeda becomes a stable member of the cosmic population. Its stars continue orbiting quietly. Its central black hole remains a gravitational anchor. Its halo of dark matter provides the structure necessary for the galaxy to maintain its shape. The tidal tails that once stretched outward dissolve into the background. The starburst regions fade into clusters of aging stars. The chaos gives way to calm. The identity of Milkdromeda is not defined by dramatic features, but by the quiet stability that follows from the long, slow blending of two enormous systems. The galaxy becomes a single entity, no longer two spirals approaching each other, but a unified structure shaped by the natural outcome of gravity acting over extraordinary timescales. Its stars tell the story of its origin, some from the Milky Way, some from Andromeda, some born during the merger, and others formed long before humans ever looked up at the sky. Together they create a new environment with its own patterns, history, and future. When the Milky Way and Andromeda have finished their long process of blending into Milkdromeda, the galaxy that emerges doesn't appear as a frozen sculpture or a fixed arrangement of stars. It's a structure shaped by gravity and motion, a structure that continues to evolve long after the merger has settled into something recognizable. To understand how gravity shapes the final architecture of this new galaxy, it helps to picture gravity not as a force that acts only in brief moments of interaction, but as an ongoing process that sculpts the flow of stars, gas, and dark matter over billions of years. The final arrangement is not something gravity imposes all at once. Instead, it is a natural result of the way every star, cloud, and cluster follows the path that gravity presents to it. In the early stages of a galaxy merger, the gravitational field is constantly shifting. Stars are tugged in various directions. Gas clouds lose their familiar orbits and drift inward. Dark matter halos slide through one another, creating a combined gravitational landscape that no longer resembles the one either galaxy began with. But as time passes and the chaotic mixing slows, the gravitational potential becomes smoother. The combined mass of both galaxies, along with all the stars formed during the starburst epochs, begins to redistribute into a stable shape. This stable shape is the foundation of Milkdromeda's architecture. This shaping process begins deep in the galaxy's core, After the two supermassive black holes merge, the centre becomes a region defined by a very deep gravitational well. Stars near the core respond by adjusting their orbits. Some stars move inward, drawn closer to the new central mass. Others, especially stars flung outward by interactions with the black hole binary during its inspiral, travel into wider orbits. The end result is a central concentration of stars forming a dense region that anchors the rest of the galaxy. This central concentration is larger and more massive than the Milky Way's bulge ever was, because it contains the combined core stars of both galaxies plus many stars formed from gas driven inward during the merger. Around this core, the orbits of stars gradually settle into patterns shaped by the new gravitational field. In the Milky Way, most stars had orbits that were roughly circular and aligned with the disk. In Andromeda, the same was true. But after the merger, there is no disk, no simple plane that defines the motion of most stars. Instead, the orbits become more three-dimensional. Some are elongated, stretching far from the centre in one direction and looping back in another. Others loop at odd angles, tilting above or below the old galactic plane. Over time, these orbits fill out the shape of an elliptical galaxy. Even in this apparently random motion, the stars follow rules. They move in smooth paths that reflect the combined gravitational influence of all the mass around them. The structure that emerges is not random at all. It is the natural equilibrium state that gravity moves systems toward when their original rotational order has been disrupted. Most stars end up in orbits that no longer form an orderly disk, but instead fill a more spherical or oblong region. The overall effect is to create a galaxy that is thicker, rounder, and more balanced across its dimensions. The outer regions of Milkdromeda are shaped by a similar process. During the merger, tidal tails sweep vast arcs of stars outward. These stars do not remain in neat trails forever. Over millions of years they drift away, their individual motions gradually pulling them out of the tail. Some fall back into the merged galaxy. Others continue moving outward until they become part of the outer halo. The halo is a huge, diffuse region that can extend hundreds of thousands of light years from the centre. It contains not only stars from the original galaxies, but also remnants of dwarf galaxies that the Milky Way or Andromeda absorbed long before the merger. It holds globular clusters, dense, ancient groupings of stars that now orbit the larger galaxy's centre. It also contains faint streams of stars that trace the orbits of long-past interactions. Gravity shapes this halo by allowing stars to settle into long, looping orbits that gradually fill the available space. These orbits are not uniform. Some stars travel in tight paths close to the core. Others move along broad trajectories that take them far into the outskirts. Over time, the distribution of stars becomes smooth, even though it began as irregular fragments. The halo becomes one of the quietest, oldest parts of the galaxy, shaped by stars that have spent billions of years responding to the slow, steady pull of the whole system. Dark matter plays a critical role in this architecture. The halos of dark matter surrounding the Milky Way and Andromeda merge to form a single, massive halo. This dark matter halo is far larger than the visible galaxy. Its gravity shapes the motions of stars even in the outer regions where starlight becomes sparse. Without dark matter, the galaxy would not hold together in its final shape. The speeds at which stars orbit would not match the visible mass alone. But with dark matter, Milkdromeda has a stable, extended structure. The stars orbit smoothly, held in place by the gravitational influence of a halo that is invisible yet essential. The fate of gas in Milkdromeda also contributes to its architecture. Much of the gas that existed in the two original galaxies is consumed during the merger, either by starburst regions or by feeding the supermassive black holes. What remains becomes heated by the energy released during star formation, supernova, and black hole accretion. Hot gas can lift away from the central regions, settling eventually into a swollen, diffuse envelope. This hot gas does not collapse easily into new stars. Instead, it forms a kind of atmospheric layer that may remain for long stretches of time, slowly cooling over billions of years. As it cools, some of it may fall back toward the centre, potentially forming new stars in small bursts. But the overall structure remains dominated by old stars rather than new ones. Gravity's influence also determines the final rotation of Milky. While the original disk galaxies had well-defined rotational patterns, the merger disrupts this alignment. Some angular momentum remains, especially in the outer regions. The new galaxy may have a slight overall rotation, but nothing like the ordered movement of the Milky Way or Andromeda. Instead, it rotates in a more modest, uneven way. Some parts may rotate more quickly than others. Some orbits may oppose one another. Over time, these motions reach equilibrium, creating a galaxy that feels calm despite the complexity of the movements inside it. The final architecture of Milky also includes populations of stars that record the history of the merger. Some stars are older, formed long before the galaxies ever met. They carry clues in their chemical composition, heavy elements that reveal whether they formed in the Milky Way, in Andromeda, or in one of the dwarf galaxies consumed along the way. Other stars are younger, created during the starburst epochs when gas was compressed into dense pockets. These younger stars often cluster together at first but eventually disperse. Their ages trace the most active phases of the merger. Together, these populations form a layered history throughout the galaxy, like the rings inside a tree trunk. Another part of the architecture involves the globular clusters. Many survive the merger, though their orbits change dramatically. Some end up closer to the centre, drawn inward by the deeper gravitational well. Others are thrown outward, becoming long-term members of the halo. Some clusters may even merge with each other if their orbits bring them close enough. Over time, these clusters form a halo-wide population that reflects both galaxies' original systems. They are among the oldest structures in the galaxy and continue serving as anchors for understanding its past. Gravity also influences the distribution of stellar velocities. In a spiral galaxy, most stars move with the disk. Their velocities are organised and predictable. In Milky, this order is replaced with a broader distribution. Some stars move rapidly in long orbits. Others remain closer to the centre, moving more slowly. The spread of these velocities is one of the defining characteristics of an elliptical galaxy. It reveals not chaos, but a new kind of equilibrium, one in which stars follow their own paths while still contributing to the stability of the whole. The architecture of Milky is not static. Even after the merger is complete, gravity continues shaping the galaxy. Encounters with small dwarf galaxies passing nearby may disturb the outer regions. Streams of stars from these systems may weave into the halo. Gas falling inward from the outermost regions may form new stars. The central black hole may capture material slowly, releasing energy that heats surrounding gas. All these processes unfold gradually, but they contribute to the ongoing evolution of the galaxy's structure. Gravity keeps working, not to create upheaval, but to maintain balance. As Milky settles into this long era of stability, its architecture becomes more predictable. The centre remains bright and dense, the outer halo remains extended and faint. The intermediate regions contain stars in a range of orbits that blend smoothly from one region to the next. The overall shape remains somewhat rounded, perhaps slightly elongated depending on how the angular momentum of the original galaxies persists. Over billions of years, this structure persists, a quiet record of the merger that shaped it. Understanding how gravity creates this final architecture highlights the broader theme running through the entire story of the Milky Way and Andromeda. Even though the merger sounds dramatic, gravity ensures that the result is balanced, coherent, and stable. Stars follow the path set for them. Gas flows where gravity guides it. The black hole settles at the centre. The dark matter halo supports the whole system. Nothing is wasted, nothing is lost, and nothing is random. It is a system that reflects billions of years of motion, interaction, and gradual settling. When people hear the phrase galactic collision, the mind often conjures an image of something violent. It sounds like two immense objects smashing into each other with explosive force. It sounds like destruction. It sounds like rupturing stars and shattered systems flung into darkness. But whenever astronomers describe what actually happens when galaxies meet, the explanation is quietly surprising. Galactic collisions are long, slow, almost understated events. They reshape structure on enormous scales, but they do so with a gentleness that defies the dramatic language we naturally associate with them. The transformation is profound, but not explosive. It is sweeping, but not catastrophic. The universe rewrites itself over immense spans of time, with each step unfolding so gradually that a single lifetime can't perceive the change. To understand why these collisions feel so gentle despite involving objects of unimaginable size, it helps to begin with the spaces between stars. Even in dense regions of galaxies, the distances separating stars are vast. If you picture the Sun as a grain of sand, the next nearest star would be several kilometers away. Multiply those distances across hundreds of billions of stars, and you begin to grasp the scale of emptiness that fills the Milky Way. This emptiness is not unique to our galaxy. Andromeda, too, has its stars distributed across enormous regions where the space between them is mostly empty. When these galaxies approach, their stars do not behave like crowded objects slamming into one another. Instead, they pass through each other like two swarms of insects drifting across a field, sharing the space, influencing each other's paths gently, but rarely colliding directly. The gravitational fields of the galaxies, on the other hand, do collide. Gravity extends across these empty distances, shaping the motion of stars and gas even when no physical contact occurs. When two galaxies get close enough, the gravitational pull on each side begins to distort their shapes. The outer regions stretch toward the approaching galaxy. The inner regions shift subtly as the gravitational potential changes. But these distortions don't appear all at once. They grow slowly over tens or hundreds of millions of years. If you were to watch the early stages of a merger unfold on a sped-up timeline, the galaxies would look like they were being stretched like soft dough, not shattered like brittle glass. This smooth stretching is one of the first reasons galaxy collisions appear gentle. Gravity acts continuously, not abruptly. The stars respond to the combined gravitational field by adjusting their orbits, not by crashing. This adjustment is subtle at first, then more noticeable over time, but it is always guided by the unbroken influence of gravity, which creates paths rather than impacts, curves rather than explosions. Gas behaves differently from stars. Gas can compress, heat, and collide. In a galactic merger, gas clouds are among the few components that directly interact. When two gas clouds meet, they don't pass through each other the way stars do. They collide, slow down, and become compressed. This compression can create new stars, ignite bright starburst regions, or feed supermassive black holes. But even these gas interactions do not resemble explosions. They unfold over long periods, with clouds extending over enormous distances. The heating and cooling happen on timescales so immense that nothing feels sudden. Even the most active starburst region takes millions of years to ignite, flourish, and fade. The slowness of galactic collisions is another foundational reason they are gentle. Human intuition expects collisions to be fast. If two cars collide, the moment of impact happens in fractions of a second. If two asteroids collide, the explosion occurs immediately. We instinctively imagine speed as part of the definition of collision, but galaxies move on scales that make even their fastest motions feel unhurried. The Milky Way and Andromeda approach each other at hundreds of kilometers per second, which sounds fast until you compare it to the distances involved. At that speed, the galaxies still take billions of years to fully meet. By the time they overlap, stars have completed dozens of orbits around the galactic center. Entire species could evolve and vanish on planets orbiting distant stars without noticing any shift in the sky's shape. This pace strips the collision of any sense of abruptness. It becomes a process, not an event. The next part of understanding this gentleness comes from scale. When you describe galaxies as massive, majestic, and structured, it's easy to forget that they are not solid objects. They're gravitational systems with enormous reach but very little density. Galaxies don't have surfaces. They don't have edges that can break or smash. When two systems like this meet, they interact more like fluids than solids. Instead of colliding, they flow through each other, mixing gradually. When they pass through one another the first time, they distort each other's structure but remain mostly intact. Then gravity pulls them back together. They pass through again. Each passage reshapes them further, blending their stars and gas into new patterns. No sudden rupture occurs. Instead, the galaxies pass, pull, stretch, and return in a cycle that repeats until they settle into one combined structure. Even when looking at the most dramatic images of interacting galaxies, like the antennae or the whirlpool, the apparent violence is misleading. The shapes in those images are the result of slow gravitational stretching, not physical tearing. Tidal tails, those long arcs of stars, are formed by stars drifting outward gently, not being flung out by explosive force. The curves, the spirals, the bridges they form all reflect smooth, continuous motion. These shapes are not scars left by collisions. They're trails created by stars following new gravitational paths. Supermassive black holes offer another example of unexpected gentleness. When the Milky Way's central black hole meets Andromeda's, it does not happen abruptly. The black holes drift slowly toward the center of Milkdromeda for millions of years. They move in response to dynamical friction, the slow transfer of energy from the black holes to the surrounding field of stars. When they finally become close enough to orbit each other, their dance lasts even longer. Stars passing nearby help drain energy from the system. Gas interactions may heat the surrounding region, but nothing about the process resembles the dramatic collisions black holes are often imagined to produce. Only near the final moments does the system release a burst of gravitational waves, and even then the burst would not harm anything surrounding it. The merger creates an elegant ripple through space-time, not a blast. Another factor that contributes to the gentleness of galactic collisions is the relative stability of planetary systems. The Sun, for example, will sail through the merger largely unaffected. The planets orbit the Sun because the Sun's gravitational pull far outweighs the influence of distant stars. Even if another star passed within a few trillion kilometers, which is extremely unlikely, the gravitational effect would be gentle enough that it wouldn't dislodge planets. In most scenarios, stars remain so far from each other that their local systems stay intact. The solar system continues its orbit around the core of the new galaxy, drifting in a slowly shifting gravitational field, but remaining structurally unchanged. This reinforces the idea that galactic collisions do not destroy the systems inside them. They rearrange the galaxy's large-scale structure, but the smaller structures within it remain surprisingly unaffected. The gentleness also comes from the fact that galaxies are not rigid. They don't break, they don't crack. When a solid object collides with another solid object, stress builds up at the point of impact, creating fractures or heat. Galaxies avoid this entirely because they consist mostly of empty space and gravitationally bound material that responds fluidly to forces. Stress, in the sense we imagine it in collisions, doesn't accumulate. Motion simply shifts. Trajectories reroute. Orbits change their shape. Gravity redistributes mass smoothly. It's not a process of breaking down. It's a process of blending. When observing real interacting galaxies across the universe, astronomers see these gentle signatures everywhere. They see long tidal tails arcing outward. They see starburst regions igniting quietly. They see cores moving closer together over billions of years. They see material drifting slowly inward or outward. Everything matches the idea of a merger guided by calm, persistent gravity rather than sudden violence. It's also worth reflecting on the way time plays a role in our perception of gentleness. Human senses are tuned to react to quick changes. Lightning strikes, waves crash, Vehicles accelerate, explosions surprise. These are the scales we understand, but galaxies operate on timescales far beyond our intuition. A fast process in a galaxy may take millions of years. A violent rearrangement might unfold over billions. When changes occur that slowly no star notices, no planetary system feels it, no structure is torn apart because the timescale is too vast for stress to accumulate. Everything has time to adjust as gravity shifts the balance around it. The gentleness extends even to the final shape of the merged galaxy. Milkdromeda emerges not as a shattered collection of debris, but as a calm, settled structure. It is rounder, smoother, and thicker than the original spirals, but it is coherent and balanced. The stars orbit in new patterns that feel quiet despite their complexity. The galaxy glows with the accumulated light of hundreds of billions of stars, many of which formed long before the merger ever began. Nothing about the final structure suggests trauma. Instead, it suggests continuity, evolution, and the natural progression of gravitational systems over time. Even when small dwarf galaxies are absorbed by larger ones, the process is gentle for similar reasons. The dwarf galaxy experiences stretching, its stars gradually pulled into the halo of the larger galaxy. Over time, the dwarf dissolves into the background population. Streams of stars trace its orbit for a while, then fade into the larger halo. No rupture, no explosion, just slow redistribution. The universe seems to prefer this quiet choreography. The idea that galactic collisions are gentle may feel at odds with the scale of the systems involved, but it aligns perfectly with the physics of how matter moves through space. Gravity doesn't push or strike, it pulls continuously. It shapes trajectories without shattering what it touches. It creates structure without tearing anything apart. Even the most dramatic cosmic transformations are driven by this same quiet influence. After billions of years of drifting, stretching, blending, and settling, the universe leaves behind structures that are more than rearranged galaxies. They are reminders of how even the largest changes in the cosmos can unfold with a softness that feels almost peaceful when seen across deep time. When stepping back from the long story of the Milky Way and Andromeda, it becomes easier to see the merger not as a single event, but as a slow, evolving landscape of motion and change. There is no moment where the sky suddenly shifts, where stars rush toward one another, or where the galaxy fractures. Instead, the universe unfolds its transformations across timescales so large that human intuition struggles to follow. What becomes meaningful in a story like this is not the collision itself, but what it reveals about how the cosmos behaves. The ending of this tale offers more than a picture of a future galaxy. It offers a way to think about our own place in a world that moves constantly, quietly, and with an order that doesn't ask to be noticed. By the time the Milky Way and Andromeda have blended into Milkdromeda, the Sun, if it still exists, would be in a late stage of its life or long past it. The Earth, whether transformed by the Sun's expansion or no longer present at all, would not be a witness. Humanity, if it ever spreads beyond Earth or continues in new forms, would see the cosmos from some future vantage point. But the story of the merger is not just about the fate of one planet or one species. It's about how every part of the universe continues evolving whether or not anyone is there to see it. Thinking about the far future often brings a mix of curiosity and distance. These events unfold so slowly that they almost seem hypothetical, unreal, or purely imaginative, but the physics behind them is as grounded as anything we can observe in the present. The forces shaping the merger are the same ones that guide the planets around the Sun, the same ones that hold galaxies together, and the same ones that influence the earlier structures after the universe began. The collision between the Milky Way and Andromeda is not an exception to the rules of the cosmos. It is one of the most natural consequences of how gravity shapes large systems. From the perspective of a distant observer, the entire merger might look like a gentle blending of two luminous spirals into a larger, smoother galaxy. From any individual star's perspective, the galaxy's transformation feels like a quiet shift in the background. These two ways of seeing the event highlight something fundamental. Our interpretation depends on the scale we choose. On human timescales, everything appears calm and unchanging. On cosmic timescales, everything is always in motion. The stars drift, the galaxies evolve, the universe expands. There is no fixed moment. Every point in time is part of a larger flow. Reflecting on this idea can bring a surprising kind of comfort. The universe is full of movement, but the movement is patient. It allows structures to persist long enough for life to emerge, for planets to form, for stars to age naturally. Even in a galactic collision, something that sounds overwhelming, the process creates new stars, new structures, new chances for worlds to arise. The story is not one of destruction but of transformation. What existed before becomes part of something larger, something new, something shaped by the same forces that sculpted the galaxies in the first place. There is also something grounding in the idea that cosmic events continue without requiring our involvement. Whether or not anyone observes them, galaxies merge, stars are born, planets orbit their suns, nebulae spread their gas across space. The universe does not rush, it does not pause, it maintains its quiet rhythm. This perspective offers a wider frame in which to place human concerns. It doesn't minimize them, but shows how they fit into a larger world where change unfolds slowly, predictably, and without urgency. The galaxy's merger becomes a reminder that grand transformations can happen without violence, without abruptness, and without losing the coherence of the whole. Imagining a distant civilization watching the merger from within Andromeda gives the story another layer. They would inherit a sky shaped by events that began long before their existence. They might study the faint streams of stars that mark the remnants of tidal tails. They might observe clusters with ages that trace back to the starburst epochs. They might develop their own ways of understanding the structure of the merged galaxy, building stories or science around the arrangement of stars they see. For them, the history of the Milky Way and Andromeda would be something they deduce from the patterns that gravity left behind. If any such future observers could look back in time, they would see the universe as a continuum. The Milky Way did not exist forever. It emerged from the clustering of matter in the early universe, grew through mergers, absorbed smaller galaxies, and evolved into the structure we see today. Andromeda followed a similar path. The merger between the two was not a break in that history but another step along the same curve. Andromeda would grow older, eventually encountering other galaxies in the far future. The story would continue. The universe does not mark beginnings and endings the way humans do. It flows from one phase into another. One of the most interesting aspects of contemplating a cosmic future is realizing that the universe is not static, even on the larger scales. Galaxies drift toward one another because of their mutual gravitational attraction, but the larger universe continues expanding. Over time, galaxies not bound to each other drift apart faster and faster. The Milky Way and Andromeda merge because they are close enough that gravity overcomes the expansion between them. But other galaxy clusters will grow more distant. Eventually, many galaxies will pass beyond the horizon from which their light can reach us. A far future observer living inside Andromeda might see a sky where the local cluster remains visible, but more distant galaxies fade from view as the universe expands faster than light can cross the increasing distances. This idea deepens the meaning of the merger. It becomes a rare gathering of material that gravity manages to bring together despite the universe's overall expansion. Andromeda will not be one among countless nearby galaxies. It will become the dominant structure for anyone living inside it, a grand island of stars floating in a vast and darkening universe. This isolation makes the merger even more significant in the long-term story of cosmic evolution. It becomes the final blending of nearby galaxies before the expansion grows too strong for future mergers to occur on similar scales. Thinking about this far future also shifts the focus from the galaxies themselves to the way the universe works as a whole. It's not just about stars merging or gas clouds collapsing. It's about how space-time expands, how gravity counterbalances that expansion in local regions, and how the larger structures are shaped by the interplay of forces that never stop acting. The Milky Way and Andromeda merge because gravity gathers matter together, creating larger and larger structures until the scale of the universe's expansion outruns the process. In a way, the merger is the universe's last opportunity to build something of this scale in our region of space. When reflecting on what it means to witness, or imagine witnessing, a cosmic future like this, the perspective becomes both humbling and expansive. It reminds us that the universe is far older and far larger than any individual story. But it also reminds us that our understanding of it is built from moments of looking up at the sky, moments where the stillness overhead gives the impression that nothing changes. That stillness is temporary, but only on scales so vast that our lifetimes don't capture the motion. This contrast between the sky's quiet, familiar appearance and the enormous transformations happening slowly across the cosmos is part of what makes reflecting on the future so compelling. There is a kind of peace in knowing that the galaxy will continue evolving long after anything we understand today has faded. The motions of stars will continue, the drift of gas will continue, and gravity will keep shaping the paths that matter takes. Even when galaxies collide, the process will be gentle enough that stars maintain their orbits, planets continue circling their suns, and the new galaxy finds a stable structure. In a universe often imagined as violent and unpredictable, the reality is a long sequence of steady, predictable shifts. If someone, far in the future, were to look back on the Milky Way and Andromeda as ancient structures that once existed separately, their understanding would come from the patterns preserved in the stars. They would see streams of material wrapping around the halo. They would find clusters with chemical signatures from two different origins. They would piece together the history of the merger in the same way we piece together the stories of distant galaxies today. The cosmos keeps its own kind of memory, written in the motions and compositions of the stars that survive each era. As the story of the Milky Way and Andromeda comes to its quiet close, the deeper message is not about the details of the merger, the shapes of tidal tails or the paths of black holes. It's about how the universe changes. It changes slowly, steadily, and with a balance that extends across time in ways that bend our intuition. The merger shows that even the largest transformations can be gentle, even the grandest scales can be patient, and even the future can be shaped by calm, orderly forces rather than sudden disruption. The cosmos has room for both permanence and change. Stars burn for billions of years but eventually fade. Galaxies maintain their structure but eventually merge. Planets orbit their stars but drift slowly through shifting gravitational landscapes. Everything has a rhythm, and everything participates in a larger motion that continues long after individual moments pass. Witnessing a cosmic future like the merger of the Milky Way and Andromeda, if not literally, then through imagination, gives a sense of the scale on which the universe operates. It invites a sense of awe not because the event is dramatic, but because it shows how easily enormous systems can shift without breaking. It shows how gravity acts as a quiet guide, moving matter along paths that create new structures instead of destroying old ones. And it shows how the universe's evolution, for all its vastness, is consistent with the same gentle laws that govern the motions of planets, the fall of objects, and the flow of time. In the end, the story of this merger is a reminder that the universe is always moving, always reshaping itself, always creating new forms. It's a story that continues long after the present becomes the past, long after stars exhaust their fuel, long after the structures we know have evolved into something unfamiliar. And it is a story that will continue, quietly, patiently, and steadily, as the cosmos unfolds across the deepest stretches of time.